this two-day online workshop on hyperspectral remote sensing and its applications. Thank you for being a part of this workshop.
Hello. Am I audible?
Yes, ma'am, you are audible.
Honorable Director Research, Satyabama Institute of Science and Technology, Dr. P. Sheila Rani, respected Chief Guest, Dr. Reddy Narayan Sahu, Indian Agriculture Research Institute, New Delhi, key speakers from national and international institutions, Dr. Roshan Srivastav, Director, IIT Tirupati, Navavishkar Innovation Foundation, and all the participants from academia and research, colleagues and friends. A very good morning to one and all. I'm happy to welcome Director Research, Satyabama Institute of Science and Technology, Dr. B. Sheila Rani, who gave all his support and encouragement for organizing this workshop. Respected Chief Guest, Dr. Reddy Narayan Sahu, Indian Agriculture Research Institute, New Delhi, gladly accepted the invitation and agreed to give the inaugural lecture and guest lecture in the midst of his busy schedule. It gives me immense pleasure to welcome Sir to this program. We have eminent speakers from reputed institutions from India and abroad with vast experience in their field. We cordially greet our speakers, Professor Giovanni Lenni, Earth Observation Satellite Image Applications Lab, Italy, Professor M. Angelo, Director Research and Development, JNTU Hyderabad, Mr. Vinay Kumar, Scientist, Indian Institute of Remote Sensing, ISRO, Dehradun, Ms. Aspa Siddiqui, Scientist, Urban and Regional Studies, Indian Institute of Remote Sensing, ISRO, Dehradun, Dr. Vaibhav Gar, Scientist, Water Resources Department, Indian Institute of Remote Sensing, ISRO, Dehradun, Mr. Justin George, Scientist, Agriculture and Soil Department, Indian Institute of Remote Sensing, ISRO. They gladly accepted our invitation in the midst of their busy research and academic schedule, and they are present in this platform. We are very fortunate to get the pioneers in the field of hyperspectral remote sensing for this workshop. We welcome Dr. Roshan Srivastav, IIT Tirupati, for giving Satyabama this opportunity to organize this workshop in this manner. I also welcome Navavishkar Innovation Hub Foundation team, Ms. Gomti and Ms. Devi, who were giving all the needed support for the successful conduct of this workshop. I welcome the coordinators, Dr. P. Mohana and Dr. Velmurugan, my colleagues who work for the success of this program. I also welcome all the scientists and faculty members to this inaugural workshop. The participants are the most important part of the workshop, who set apart 2 days exclusively for this program. Please interact with the speakers and make use of the opportunity in the best possible way. We are extremely delighted for the 2 days workshop, which is going to be a great success. Once again, on behalf of the Center for Remote Sensing and Geoinformatics, I feel privileged to welcome you all to the 2 days workshop on hyperspectral remote sensing and its application. Thank you. The special guests will be introduced by Ms. Gomti.
Ma'am, there is a lot of noise from your microphone.
Can everybody hear me? Yeah. So thank you, ma'am. Thank you so much for the warm welcome address. Now, I take this opportunity to introduce our special guest for the day, Director Research, Dr. B. Sheila Rani from Satyabama Institute. Uh, from Satyabama Institute. So Dr. B. Sheila Rani, with a passion towards teaching, she started her career in 1989 as a lecturer and has been with the institute for over 27 years in various academic and leadership positions as a professor, faculty, head, and as dean research. With a strong technical expertise, she acquired MS and PhD degree from Anna University College of Engineering, Chennai in 2001. By virtue of working for a considerable number of years in the academic and research arena, she reached the position of the Vice Chancellor at Satyabama University and assumed office in April 2011. After the successful completion of the term period as a Vice Chancellor, by 2017, assumed the post of Director Research. It's a really a beautiful journey, ma'am. She has contributed to the areas of image processing, evolutionary computing, and machine learning with more than 190 publications in referred research journals. As an active researcher, Dr. B. Sheila Rani is associated with many research organizations. She plays a vital role as the research coordinator of Satyabama University. She attracted a number of research projects from many scientific research organizations and ministries. She served as a principal investigator for over 22 sponsored research projects worth 300 lakhs. She is a research coordinator for major projects funded by Technology Business Incubators, DSD, Ministry of Steel, Earth Science Technology Cell, Ministry of Earth Science, worth 10 crores. Wow, great, ma'am. Thank you. And one of the most interesting things, she was the mission management in charge of Satyabama Sat, a micro experimental satellite developed by students and faculty of Satyabama University to collect data on greenhouse gases. It was launched along with Catosat 2C satellite PSLV C-34, and the team had an opportunity to meet the Prime Minister Narendra Modi, who appreciated the efforts of the team in building a satellite to collect data on greenhouse gases and made specific mention in his monthly Mann Ki Baat. She guided 16 doctoral candidates, of which 11 of them have successfully completed and received their degrees. She conducted a large number of short-term courses in image processing as a part of continuing education program for the benefit of working engineers, scientists, and teachers. She's also been a life member of various professional bodies and associated herself in administrative activities. She is member secretary of Indian Society of Remote Sensing, Chennai. In addition, she is also the recipient of SNT Award of University for her contribution to research and for her association in projects. She is also conferred upon the award of Distinguished Scientist by Center for Advanced Research and Design, Venus International Foundation for the year 2017. She has been to Delft University, Netherlands, Swiss Federal Institute of Technology, Switzerland, and US and NTU Singapore for fostering academic and research collaboration. Wow, ma'am. Thank you so much. Thank you for being a part of this workshop. It's a real great honor to have you here, ma'am. Now I request ma'am to share her views on this workshop. Ma'am, can you hear us?
Yeah, thank you for the introduction. Uh, Very happy to note that our Center for Remote Sensing and Geoinformatics of Satyabama Institute of Science and Technology and IIT Tirupati Navishkar iHub Foundation is jointly organizing this two-day online workshop on hyperspectral remote sensing and its applications. In fact, the coordinators or the conveners of this program, like I was very specifically asking when they were telling about this program few weeks ago, why not it could be conducted in an offline mode so that we will have a chance, like either it could be from IIT Tirupati faculty or the Satyabama faculty would have a chance to meet in person and share the infrastructure and the expertise. Of course, this is going to happen even through online also. But really, this is an opportunity to meet each of us personally, even though the participants are going to be benefited out of the lectures which is being conducted. But I generally feel any program that is being conducted in hands-on will give a more eye-opening for the students, and they would be enthusiastic enough in taking up the work further. But this is not the one that is going to stop with. This is what I was telling to my convener, Dr. Merikuti Abraham. Like, let this be a start so that over a period of time, because as far as our Center for Remote Sensing and Geoinformatics is concerned, like it has been started in association with ISRO in the year 2004. So almost more than 15 to 18 years of their experience of the scientist experience, because it is a separate center by its own, like they were involved in carrying out lot of sponsored research projects with ISRO, with Ministry of Earth Science, CSIR, and various other sponsoring agencies. So they have a huge database that is being available on the satellite data, where they are working for various types of remote sensing applications, and also they conduct lot of training programs. This is one of the highlight which I have to say for my Center for Remote Sensing. They do conduct lot of certificate programs either through DST, because ours is being considered, our Center for Remote Sensing is being considered as a nodal center for NRDMS related activities of Department of Science and Technology, Ministry of Science and Technology. So this is a continuous process in addition to the research projects they are carrying it out. So this wonderful infrastructure what they have, and the database what they have, and the students capacity what they come and utilize the infrastructure of our Center for Remote Sensing and Geoinformatics is huge. Almost as I said, for the past 18 years, the scientists were into this area. So like our association with ISRO and various other institutions also, like from University of Madras, expertise, they also were part into it in recruitment of the scientists also over here. So all these highlights of our Center for Remote Sensing make them to flourish in a very good manner in association with our own students of civil engineering, students of computer science engineering, who best utilize this infrastructure. So let me take this platform to thank the conveners for having arranged this first level of virtual mode of this 2 days workshop. So possibly again, it is a request to the conveners that they should immediately plan for another program in Satyabama, in the venue of Satyabama, to conduct an offline program with the students, so that it would make them do hands-on experience also can be given for the students. So with this, once again, my sincere thanks to the conveners of the IIT Tirupati and the top level officials of the IIT Tirupati for having joined hands with our Satyabama Institute of Science and Technology, particularly Center for Remote Sensing and Geoinformatics, in carrying out this 2 days online workshop. There should be one brainstorming session with our own scientists, if possible. You might have all fixed the program schedule. If there could be any possibility that there could be an interaction among, maybe in the virtual mode itself, maybe at the end to conclude, let all the experts of the centers from both sides can join, and there can be some small brainstorming session among themselves, so that we can think about how to take it up further. More than these workshops, any types of other collaborative research projects, it could be done. by both the institutions together. That can also be thought about it, if possible, in this itself on online as a brainstorming session, or maybe in a later period we can have an appointment clearly, and we can either you people can come here, or we are also prepared to come there, and we can have a detailed discussion and start carrying out some sponsored research projects. This is one of my opinion, which I already shared with my convener. Maybe this I am putting it in this platform. So once again, my sincere thanks with the participants who have joined in this program and who would be benefited out of it. Wishing you all the best. And once again, my sincere congratulations to the conveners of both the institution who is taking this program forward. Thank you.
Thank you, ma'am. Thank you for putting your views to us. Definitely, as you said, we will try to make a offline session where we will be either students from Satyabama will be coming to Tirupati, or we will be coming to Satyabama Institute. And definitely, I think this program will definitely take it to the next level. As you said, this is just a beginning. So, yeah.
Thank you.
Thank you, ma'am. Thank you so much. Next, I would like to take this opportunity to welcome our guest of honor, Dr. Rabinarayan Sahu, sir. Dr. Thank you, sir. Thank you for being a part of our TIH program. Actually, Sahu sir has been like the backbone for TIH. He has been supporting TIH for a very long time. And also he has been a part of our previous programs, sir. So thank you, sir. Thank you for your extended support to our institute. Thank you so much. So I take this opportunity to introduce Sahu sir. Dr. Rabinarayan Sahu sir is working as the principal scientist in the Division of Agricultural Physics at Indian Agricultural Research Institute, here, New Delhi. He has more than 22 years of experience in research, teaching, and capacity building in remote sensing and its applications in natural resource management. His major research interest is in remote sensing applications in agriculture, such as imaging spectroscopy for soil and crop health monitoring, precision farming, plant phenomics using sensors at ground, air, and satellite platforms, and drone remote sensing. He has a rich experience in generating and mobilizing resources to lead different multidisciplinary and multi-institutional collaborative remote sensing research programs through 10 different external funded projects, which was total amounting up to 1,500 million rupees. He was co-leading a network program on imaging, spectroscopy, and its applications for DST, having 37 centers involving ICAR, IITs, universities on 7 thematic application areas. At present, he is a program leader leading ICAR network program on precision agriculture and involving multidisciplinary team from 16 ICAR institutes. He has published more than 240 publications, having 120 research papers in referred national and international journals, mostly on remote sensing applications and applications in agriculture. Great, sir, great, beautiful journey. And he has been a member of Advanced Working Group of Department of Science and Technology on Hyperspectral Remote Sensing. He's been a member to Science Campaign of ISRO, JPL, NASA, Airborne Hyperspectral Remote Sensing in India, and a member secretary of Task Force Group 1 on Drone Remote Sensing for Agricultural Insurance of Niti Aayog, Government of India. He's been a member of the Technical Expert Committee of DST and BIRAC DBT. Dr. Sahu's work on UAV-based remote sensing for soil and crop health was showcased to Honorable Prime Minister of India during March 2016 and 2018. He has also been a visiting faculty to University of Nebraska, USA for remote sensing-based agricultural drought monitoring. He was being deputed to United Kingdom, Japan, China, Thailand, Luxembourg, and USA for deliberation on cutting-edge technologies for smart and precision farming. Thank you, sir. Thank you for being with us. It's really a beautiful journey you have come all the way. So I'm now I request you to give your guest of honor note and also to preside this whole workshop now.
Thank you, Gomti, and a very good morning to all the respected members on the screen over here. Madam Sheila Rani, Director Research at Tevama University. I have been there for maybe 10 years back under a DST program. Dr. Murli Mohan, myself, and many team from IIT Bombay, we were there. We had two faculty who were very active involved from your side for that purpose. And you had a great hospitality for us. Thank you very much for that.
Thank you, sir.
And, I must congratulate and to Dr. Roshan, who is the mastermind all about this program, and also the TIH coordinator, Ma'am Gomati, and whole team for starting this program on hyperspectral remote sensing, at least starting online. And then, as ma'am was saying, we should have a physical training which will be more effective and efficient for the fellow participants. And I can see, I think since it's little early morning, 36 participants already there. But I think it's the most demanding and training program what I have ever seen. I have conducted more than 12 programs on different aspects, again, imaging, spectroscopy, and applications funded by DST and ISRO. Always I see there is a huge demand and applications. And I must say, Dr. Roshan, it's a wonderful idea to start with such a program, though online, but it will be very effective. At least theoretically, you will be able to show. Practically, it's going to be very difficult to show some of those analytics or instrument what you would like to. I think very soon, I think Roshan has in mind physical meeting either with at Satyabama or together with IIT Tirupati, so that it will be more effective. Ma'am, the imaging spectroscopy or hyperspectral remote sensing is one of the very cutting edge area with respect to space technology, with respect to sensor advancement. So, and there are very few remote sensing community who have been working on hyperspectral remote sensing. As of now, the possible reason is the lack of capacity building resources, because this is we call, or many countries they say it's a luxurious research in case of remote sensing, because the very expensive sensors are very, very expensive, starting from the ground to airborne or to satellite. If we talk of ground hyperspectral remote sensing, the cost ranges starting from minimum 30 lakhs to 70 to 80 lakhs ground non-imaging spectrometers. So, but if you go to airborne, it starts with 50 lakhs, ends up with something around 3 to 4 crores. So you can think of the kind of program you need to have this kind of facilities to take up, and that's what the challenging area where we are not able to build up a common facility at many places. And keeping that in view, we had a network program funded by DST. We had 4 centers at the 4 corner of country, where we created a central facility with respect to hyperspectral remote sensing. One at Delhi, one at Kharagpur, one at Bombay, one at Trivandrum. So with having all those facilities, which was under the aegis of DST Big Data Analytics Division, ICPS division right now. So that was the purpose. Second is, in the meanwhile, we have got a blessing in disguise, the airborne campaign with the NASA. So we got huge data, airborne data available to us for many applications, for many purposes. So that was the really great benefit to many research community to start with that free data. So, and again, we have also long journey with respect to satellite remote sensing. Again, we have some of those sensors where we have hyperspectral sensors. So coming back to this training, I think the well designed with respect to basics of remote sensing, hyperspectral remote sensing, to sensors, to the satellite, and various applications, so that people, whatever the data is available, either on the archive or on some of the free sites, that can be played with. And the purpose of having hyperspectral remote sensing is, if at all from this hyperspectral we can come down to low cost sensor, multispectral, or something which is useful for different applications in different thematic areas. As Ma'am Gomati was saying, we have been working with 37 institutes with the 7 thematic areas, understanding what is the capability of this. There are many national programs, how we can bridge with those national programs using these advanced sensors, at least developing some low-cost sensor. For that purpose, we need this kind of sensors to understand how the interaction takes place with respect to EMR and target, so that we can find out some of those specific ranges to develop some kind of low-cost sensors in collaboration with the private partners or startups. That's the purpose of having TIH over here, so that with the public-private partnership, we can come out with. I think this is one of the major purpose of having TIH again under ICPS division, and that's the reason I think Professor Roshan started with the Hyperspectral to come up with. So I don't think I need to talk more on this right now. I think uh, the whole 2 days there will be wonderful deliberations by wonderful, very known authority on the subject domain, speakers from different background, and my colleagues from Indian Institute of Remote Sensing and ISRO, and also many other organizations. They will be there. I think it will be very, very effective and impactful. I think with all the best, I must say again, congratulate the team to conceptualizing and initiating this kind of program with the institute in collaboration with the Satyabhama University, who are the great host always. Thank you. Thank you all.
Thank you, sir. Thank you so much for sharing your views. I think that will be really helpful for us. Now, I take this opportunity to welcome our project director, Dr. Roshan Srivastav, sir. He's been the roots of TIH. He has started TIH and took it to this level, and he's been a constant source of encouragement and always gives the right directions to us to how to go about. So welcome, Dr. Roshan sir. And
yeah, thank you, Gomati. Thank you, ma'am, for being here as a part of this workshop. I would like to thank Sahu sir for also being part of this workshop. In fact, I think the next 10 minutes, I'm going to make a presentation where I think even the Satyabhama Institute or any institute where the participants are are present here would like to know what is this Technology Innovation Hub about and what kind of a programs are possible. I think whatever you have put up, ma'am, I think a lot of things can be possible in this area. A lot of collaboration is possible with the Technology Innovation Hub. And Sahu sir has been the key architect for this program. I think I've been personally interacting him when the idea came, like, okay, hyperspectral we have to do. And he was the one person to kind of, go and talk to him and get the information. He was readily supported us right from the design of the program, what should be the content of the program. I think I would like to thank Sahu sir for this, being an architect for this entire program, what we see today. I'll take 5 minutes to present about the Technology Innovation Hub. Can you share the slides, please? I would also like to take an opportunity to thank all our participants who are here. We have about 60 plus participants who have registered. I can see about 40 participants already online. Okay, how do I change the slides? Okay, next. All right. So where did it start all this? What is Technology Innovation Hub? Basically, it's a national mission on interdisciplinary cyber physical systems, where Government of India has allocated about 3,600 crores to kind of establish 25 technology innovation hubs across the country. As you can see that most of the hubs are established with IITs, some of them are with triple ITs, and also some private institutes like BITS. These technology innovation hubs are established. The main idea of being creating this technology innovation hub is the most of the imports what we see today, most of the areas where we are focusing today is on the cyber physical world, where we are kind of connected with the cyber and our physical. As you see, like we are very well connected with the mobile phones, very well connected with the technology, and this is where government of India thought like, okay, this should be an area where we should focus, and we become down the line in 10 to 15 years very much kind of self-reliant on these technologies, like an Atmanirbhar program into these cyber physical systems. So at IIT Tirupati, we got positioning and precision technologies. This is basically dealing with remote sensing, GIS, and non-invasive technologies, what we see today in medical science, we have been seeing at the airports. So this is one of the areas which we have got it, the Technology Innovation Hub at IIT Tirupati. And all the, when I'm talking about the Technology Innovation Hub, basically I'm representing the other 25 hubs. And most of the hubs, what you see, the only difference will be the area of cyber physical systems. Otherwise, the support, the programs, what we are doing should be very similar. And if you feel that there is any other hub which is kind of supporting to your area of research, I think you should be approaching the respective hubs. All the hubs what we have is basically registered as a Section 8 company. So we are an independent entity. We have registered it as an IIT Tirupati Navavishkar iHub Foundation. Basically, the hub is all about four major objectives. What we do is we kind of support in technology development. Basically, it's a translational research, taking your research to product and then product to market. So this is what the major focus, one of the major focuses. The second one is human resource and skill development. I'll come back to this in the later slides, what we are doing. Then the third one, which is very important for any of the hubs, is creating the startup ecosystem. Today we talk about students not looking just for the jobs, but they are very young, talented students who would like to become part of this business world. So there are a lot of opportunities in the startups. As a section, as a technology hub in positioning and precision, we have diversified ourselves in these areas. As you see on the list, we have something on technology, what we are working. Again, I say that this is not an exclusive list. These are some of the core areas what we thought like we should be working on, like quantum-based positioning, remote sensing, SAR interferometry, which is one of the hyperspectral imagery, LiDAR. So this is something. What we have done is we kind of went around and thought like what kind of a problems we should be focusing on. The positioning and precision is a huge area, but as a hub, we thought like what could be the major areas which we should kind of try to work on. So we have sent it across country, asked various experts like what areas we should focus on. So you can see about 8 problem statements what we have kind of collected from the experts. One is looking at atomic clocks with improved time localization, navigation sensors for satellites, and IoT and embedded hardware. So this is on the positioning side. Then when you look at the one which I think today we are focusing is on mostly geospatial data applications and processing. Having this technology of hyperspectral, multispectral, LiDAR, cloud point data, how do we use them? What kind of an end products we can create? So this is some of the areas which I think we are going to focus. Again, this is not an exclusive list. Anyone who is working in these areas can please come forward and then put a proposal for the technology development, skill development, or any other 4 objectives. The areas what we focus is in defense and navigation, quantum technologies. The one more area is indoor positioning, which is now gaining a lot of popularity. As a young student, if you are kind of listening to this, then there's a tremendous kind of market for the indoor positioning, what I see. The area of applications, again, positioning and precision is going right from a common man to satellite. So there are a lot of areas where you can fill in. This is one area where there's not specific to any engineering group. It can be from computer science, you can be from electrical, you can be from civil engineering, you can be coming from science. So this particular technology innovation hub actually covers a very multidisciplinary, cross-disciplinary application. So you can make a nice group of people who can come together and develop the applications. Okay, this is what I thought, like I'll spend about a minute or so on this. This is the most important slide of the what we do, what kind of an opportunities we have. First, if you are a faculty, if you are a startup, and if you are a scientist and you would like to develop any technology, this is not a research proposal call. This is a technology development where you need to focus on product development. We call it as technology readiness level should be greater than 4. That means it's a at least lab demonstratable product at the end. You can create the softwares. When I say product, doesn't mean it's a physical product. You can also be working, like most of the geospatial applications can be a mobile apps, can be a software, desktop, cloud-based. So there are a lot of possibilities. So the website link is there. There are a lot of call for proposal is open 24/7. Uh, there are a lot of funding opportunities in this, but please make sure that this is not like a research proposal. It is more on a product development where you shift your focus from research to product to then to take it to the market. When I say market, we are kind of trying to work on startup ecosystem and entrepreneurship, where we have a lot of funds to support number of startups, and the seed funds can go up to rupees 1 crore. It all depends on what is your idea and how well you're placed into the future market. We'll be able to fund, not even from our funding what we have, but also we'll be able to bring in other investors. In fact, our CEO, Mr. Srinivas, is able to connect a lot of investors from both national and international level, where we're kind of making sure that when you come up with an idea, you have tomorrow future to take it to the industry also. And we do a lot of collaborations to make sure that the product what you're developing, you have industry connect, you have government agencies working around, I mean, giving us the ideas on what to work on. So there's a lot of backup is there for any project proposal you're coming forward with, even for the startup. Now, for the universities and for the faculty who are here, human resource development is an attractive plan what we have. We support graduate internship about 10,000 per month for 10 months. So what I suggest is if you want to work on a small app development, small product development, sensor developments, this is a very great way to do it. We also kind of support PG fellowships, PhD fellowships. Now PG, UG, PhD, they need not to have to come to IIT Tirupati. They can be in their own host institute. They should be a full-time student registered in their own institute, and we'll be very happy to support. The only condition what we have is it should be related to positioning and precision, and there should be something valuable and product what we see at the end of the term of the fellowship or internship. We also have a postdoctoral fellowship. It is slightly different. We want the postdoctoral fellow to be part of our system here in the TIH. So he or she has to come to Tirupati and support us. We have also something called skill development programs. We kind of jointly do a lot of programs. This is one of the programs what we kind of jointly working with Satyabhama, being one of the uh, key players in remote sensing, as ma'am was saying, since 2004, you're in this market. Open to this, but the program should be mostly very high quality. Will help you in designing it. Will be helping you to kind of make sure that whatever programs we do are up to the standard where we actually create an impact. So this is kind of opportunities what you have with the TIH. Yeah, as I said, a lot of activities are going on. We are very well connected with many of the ministries, state, government, private agencies. So number of possibilities are there with the Technology Innovation Hub. Again, it's just not I'm talking about our own hub. There are other 25, 24, 25 hubs where this is the same thing is happening. If you feel like you would like to get connected with them, and if you have any difficulty, please let me know. I'll be able to help you to also connect with the other hubs. Yeah, I think we have been mentored with excellent members who have been part of this hub, right from people from Vivian Krishnamurthy sir, from IST, Ajit Talgatki sir, Major General Shivakumar sir, Omkar Dikshit sir. So they are part of our team. In fact, there are so many other mentors, including Sahu sir, who's been helping us to work in these areas where we can progress very quickly and kind of achieve the mission what is meant for this technology innovation hub. I think I just exceeded 1 minute here. I say thank you. Thanks a lot for giving us this opportunity, ma'am, to collaborate and then kind of create this program. Would definitely like to do the follow-up programs. It is already part of our agenda. We'll make sure that we'll do one of the kind of hands-on sessions on hyperspectral and other remote sensing areas. Thank you. Thanks a lot.
Thank you, Dr. Roshan, sir. It was really great to know about EIH. I think a lot of people would have been uh, uh, would get an idea about EIH, and I think we will get to do many more programs. Thank you for this introduction. Now I request Dr. Sahu sir to preside the session with his lecture for the day.
Just give me 2 minutes to get my pen drive and get it ready. Just 2 minutes. Huh?
Sure, sir, no problems.
Thank you. Thank you.
Meanwhile, if any questions from the audience on the technology, participants on the Technology Innovation Hub, I'll be very happy to take.
दे दिया। चलो।
Can also post the participants can also post their questions in the question and answers chat box. Any participant who is willing to ask any questions can also can go for it now, or they can also post their questions later on the question and answer chat box. Thank you.
The screen is visible, Ram?
Yes, sir. The screen is visible.
So I am audible also, right?
Yes, sir. Yes, sir. You're on.
Okay. So very good morning to all of you, and I'm very much thankful to TIH, IIT Tirupati, Professor Roshan, and also Professor Satyanarayana um, hosting me recently in their campus. Again, it was a wonderful experience interacting with very young team, very excited team to work on. So also, I was very excited to be part of this program, and that's what Rosunu contacted. And I thought, let me talk a little bit about hyperspectral remote sensing and then overview. Thank you, Professor Roshan, and also all your team and Ma'am Gomati for facilitating for this event. And very good morning to all the participants. And so just I'll give an overview how much time I have, Roshan, so that
So you have 1 hour
okay. So by 11,
and 15 minutes of discussion we have. So you can go up to 11:35,
11:35. Sounds good. Okay.
11:40 also. Yes, sir.
So I think I don't need to talk about what remote sensing stands by, but there may be many young researchers. I don't know whether they are into remote sensing field or no. So why at all remote sensing? And you know what is remote sensing, and what is the benefit of remote sensing? And there are a number of challenges if you can see. So the process of remote sensing is given in a flow diagram. You need a light source, you need a sensor. In between there is a medium called atmosphere, and there are a lot of interactions. And that interaction is nothing but basic physics, which takes place. That is the reflections, emissions, scattering, and all those things happens. And based on that interactions, whatever the energy you are receiving in the sensor, that may be put into some few channels or large channels that decides what kind of sensor you have. And down you can see the stream, the starting from ultraviolet to radio, microwave, and radio. We have different sensors we have developed, and we have their um, possibly limitations and challenge with respect to those ranges. And you could see in between there are a lot of ups and downs. This is a y-axis is your transmittance. So you can see visible lens is almost a wonderful window to have any kind of sensor because there's a least interaction with the atmosphere. When you go beyond that, beyond 0.8, 0.9, you can see the lot of ups and downs, and because of the interaction with the atmospheric compositions like water, carbon dioxide, oxygen, and many other parameters, so aerosol. So that's the reason you have very few sensors when you go beyond sort of infrared range bands available for you to work with. And so that's the reason why we have a very discrete band multispectral channels we have in our own sensors in the satellite. So, so this is what atmosphere window concept, and based on that, you have channels decided. And you know, and the basic principle, as I said, is the basic physics is the reflectance in case of optical remote sensing, which ranges something around 0.4 to 3 micrometer. When you go beyond 3 micrometer, that is thermal remote sensing, where mostly it is governed by the Planck's law of brightness temperature, which you get. And again, the principle is nothing but the emissions. In case of microwave, again, the measurement is the brightness temperature or backscattering. It is the scattering principle which works. Again, that depends on the dielectric property of the target. So these are all basic principles of physics based on which you can the sensors works, and based on that you can get the informations. So if you look at the remote sensing, if we divide them into three categories with respect to the different sensors, so the optical remote sensing, thermal remote sensing, and micro remote sensing. As I said, you depending on the spectral range you are working, this is what three broad categories. And most of us, we are working on optical remote sensing. Very few sensors are available on thermal remote sensing. Again, very few on micro remote sensing. So today, mostly we'll be confined into optical hyperspectral remote sensing, some part in the thermal hyperspectral remote sensing also. So again, you can see the kind of interaction takes place. That's what taken from Jensen et al. 2000 from the book. You can see the kind of interaction from starting from 0.4 to 2.5. a particular base station spectra, how it interacts at the different ranges. And this is very significant when you go to when you do in optical lens and thermal lens, you don't get much of that. So again, so coming back to the number of channels or bands, what you have. So uh, there was panchromatic camera or black and white camera. Then slowly the multispectral cameras, those where you have few channels. Then we have hyperspectral where you have a large number of channels. So coming back to again the platform, all these sensors, they can be on the ground. There are sensors which are on the ground. There are sensors which can be on unmanned aerial vehicle like drones or manned aerial vehicle like some of the flights where we are piloting. Then we may have on the satellite platform. So this is what the kind of gamut of sensors available, irrespective of the energy sources, irrespective of the number of channels, and also on the platform. So coming back to the number of channels, you can see the panchromatic is nothing but a very broadband range. What you have, like you have a black and white picture, you can see IRC, IRS 1C, 1D, or even if many satellites, you will see the panchromatic camera having whole range, but very high resolution data you have. So that is what single channel you have. So then we developed with the time with the multispectral bands. That is again in between you have some ranges, like you can see the four bands over here. Again the four band, two bands over here. Again thermal you have one band. So most of the satellites, again almost 95% of satellite, they are onto this kind of number of bands. And so this is what the multispectral remote sensing. So we could see there are some limitations and challenges. Maybe follow-up slides will talk about that. So understanding that, we started working on hyperspectral. That is nothing but what you do is number of channels are getting more and more, again narrow and narrow. So that's what the hyperspectral remote sensing, like hundreds of bands you have, and they are mostly continuous. And with the time in the future, also is going to work on the ultra spectral. That's going to be, here we have something around 100 bands or whatever, maybe 10 nanometer, 2 nanometer, 3 nanometer. Now we are going to have ultra spectral having thousands of narrow bands, maybe sub nanometer level narrow bands. So this is what the evolution taken place over the time, and this is what means by hyperspectral. So if you look at the imaging and non-imaging spectrometers or sensors what are available, so this triangle tells you what are the kind of sensors we can have. For example, you have a mobile camera that is nothing but an imager which gives you special information. That's why it is called imager. The photography does. So it gives a pixel-based values, only 3 bands like RGB. There are some sensors like your thermometer which gives you intensity information. That is your radiometer. Like you have, there are many net radiometer, there are many pyranometer, there are many sensors which gives you only intensity value. What is the radiation's intensity? That is the radiometer. That is the instrument in the lab conditions. Also, you have spectrometers. That gives only spectral informations. So when you combine all possible combinations of them, so suppose you have a spectral information, same time also your imaging information, that is your imaging spectrometer. When you have spectral information and a radiation information, but not imaging, that is called spectrophotometer. For example, you can see down here, these are all spectrophotometer which are non-imaging. But when you see the spectral informations with the imaging informations, with the radiation information, that is called imaging spectrophotometer or imaging spectrometers. So most of them you can see here, these are all spectrometers which you are having here. They have all kind of information. They have intensity information, they have a spectral information, and they have also pixel based information. So those are imaging sensors. So you have on satellite based imaging spectrometers, you have airborne imaging spectrometers, and also few of them ground imaging spectrometers we have. For example, you can see here, this is called a spectrometer, this is called FTIR, both emissivity and observance spectrometer. And you can see here, this is again a FTIR, thermal range imaging spectrometer. This is a very expensive, companies tell us, which is very expensive, something around 4 crores it costs you. But it is a thermal imaging it can do. And so this is what the gamut of sensors you can have with respect to hyperspectral, what do you think of? So the possible region of getting information is the level of spectral information what you get when you get a panchromatic to multispectral to hyperspectral. You know the basic principle behind the remote sensing. That is nothing but whatever the radiations is coming back, reflecting back, or emitting back, or scattered back. That is the function of physical, chemical, and biological properties of the target is what you are looking at. So if there is a little variation in the signal, so that little variation can be addressed with respect to the composition of the material, what it has. There's a little shifting of the absorption bands or reflection. Based on that, you can characterize what that feature is, how it is. Maybe more detailed we'll be able to realize when I go further into the uh, uh, deliberations. So, so through hyperspectral, what you can do is, it's not that you only can identify that target or the particular purpose what why that absorption is taking place or reflecting, it is reflecting back, but same time also you can quantify. So what we have been doing with the remote sensing is mostly qualitative analysis. We are doing land use, land cover, and all those things we are doing, good, bad, or low, very high, all those things we are doing. With the advancement of the sensor, with the advancement of this hyperspectral remote sensing, we are able to quantify the parameter what we are looking at from the target. Maybe the turbidity, maybe the nitrogen content or water content in the leaf, maybe the fertility parameters in case of soil, maybe the grain size of the snow. Many things we can quantify because that specific interaction which takes place, they get all affected by these parameters. So based on that, you can go for modeling and can do it. So this is what the level of spectral information based on which you can quantify the abundance of the material. You can characterize whether it's a wet soil, a dry soil, whether it is a wilted. You can identify the unknown feature because you get a typical unique signatures, because this spectral reflectance is again unique. Again, you can discriminate because you have a large number of channels, more informations you have. Maybe some of the deliberations in the application, some people may be talking on about that. So I won't be able to talk all those things, but just I wanted to give you overview. So this is what the capability of a discrimination, better classification, and also detecting some of those objects which is otherwise is not possible. So coming back to the hyperspectral remote sensing definition, there are three criteria which defines what is the hyperspectral remote sensing. So one criteria is you should have large number of channels, more than 60. That is what hyperspectral is. And the bandwidth should be less than or equal to 10 nanometer, and it should be continuous. So this is what hyperspectral remote sensing means by. So large number of narrow and continuous spectral range is a hyperspectral. And you can see starting from 400 to 2500, you can see the kind of a spectral ranges. And this is what the multispectral data of Landsat thematic map where you have in between you have discrete and few of them, because as I told you, because of the atmospheric noise, the bands were not there. They didn't select that band because hardly you get any information in that band. So that's the reason. And again, why those specific bands? Because they give specific information with respect to target on the earth itself, maybe with respect to soil or water or vegetation. You will be getting typical interactions. So that's the reason why these multispectral channels has been developed or designed and launched on the satellite. So, but when you look at the hyperspectral, as I said, it is a continuous and uh, narrow. So it will be starting from 400 to 2500 continuous spectra you will be getting. So if you get the continuous bands, then what will happen? The obvious reason is that there will be some bands like here, wherever you have more interaction with the atmosphere because of water vapor, maybe because of oxygen, maybe because of carbon dioxide, maybe because of methane or ozone, whatever. So you will get a noisy in those bands. So that's the reason. One thing is you have a huge number of channels. The data is going to be really voluminous. Maybe I'll come to talk about that later. This is kind of a big data. Again, you have a challenge with respect to not simply what digital image processing you do using multispectral, same processing you can't do here, because there are two reasons. You have huge informations, large number of channels. So it's the multispectral is easy to be done, like using few variables and indices, you can do it. But here you have a huge. Another second part is in the pre-processing itself, there is a spectral noise in different bands because of the atmospheric interactions. So one has to see what the pre-processing side should do so that I can remove those channels or those channels will be useful for me for, as if at all I am working on atmospheric aerosol chemistry, I can work on that to find out some of those atmospheric parameter for my purpose. Otherwise, I need to remove them for the other applications when I look for, because those are all the noise bands. You can see in the left hand side the kind of noises what you get because of all those parameters which is in the atmosphere. So these are some of those the advantages. I'll come back to that later. Now, these are the challenges what we have with respect to hyperspectral is you have a huge number of channels, bands. Again, you have there are sufficient number of bands also which are noisy because of the atmospheric interactions, and you have to remove. So you should go for free processing of those images to get a clear noise-free channels or the image for that purpose. When you talk of imaging spectrometers, what it does, so it's a non-imaging spectrometer is, for example, I can show you here. This is what non-imaging spectrometer. You can see here the spectral signature of the vegetation, spectral signature of a soil. This is spectral signature for water. So you are getting continuous spectra starting from 0.4 to 2.5 micrometer, and you are getting continuous. Whereas you look at the Landsat images, what is that? 1, 2, 3, 4, 5, 7 given here. These are the discrete. Only few informations you have here. I think more detail I am going to talk on that later. So, and you have that kind of a physics or the chemistry, what takes place is you can see the kind of absorption and the principles, what it happens, and which parameter it interacts to, and what is that sensitive band you have. So what happens is, so you have a simple single spectra of an instrument, that is whatever the area it looks at, you will get only simple one single spectra like this. That is what the spectroradiometer or spectrometer gives you. When you talk of imaging spectrometer, that is something like each pixel, like this is an image. This third dimension is nothing but the number of bands you have starting from 400 to 2500. So this is a single pixel, what you are having here. And you click on that pixel, you'll be able to see the spectral pattern, how it goes through. So this is what the spectral signatures you are receiving starting from 400 to 2500 nanometer. So you can think of kind of a million spectrometer working on that imaging spectrometer. Each cube, each pixel is a kind of a cube. You can see number of channels what you have in the third dimension, and you click on that, you will get a spectral profile like this. So this is what the spectral data you get. So it's a huge data. So images when you capture either using drone or manned aerial vehicle, even if the satellite, is a huge data in GBs. So that's what the imaging spectrometer looks like. And you can see any particular pixel. If you look at, for example, there are 4 examples given. This is again borrowed from the book. So you can see how in case of atmosphere, what happens to the signatures. In case of soil, what happens to that particular pixel, and if it is a water, and if it is a vegetation. So click on any pixel, you'll get a typical pattern of the continuous spectrum starting from 400 to 2500, and that identifies what this feature is. So that's what the wonderful thing you have. And I think I talked about all this. So you have these are the history of the NASA's mission, in which they were looking at some of those sensors, and for that purpose they were doing all these studies to find out what is those channels which are really noisy to be removed from. And they were trying to work from 400 to 14,000 nanometer, starting from history visible to sort of infrared range, and also history thermal infrared range. So I think I covered already what you mean by imaging spectrometer. I don't need to talk more about that. I think, again, this is a basic principles of physics, where you have what is that spectrometer, where it works, something around 400 to 14,000 nanometer, what you have the data sets. And how the sensor works. Just the basic principle is, sensor is nothing but simply a grating system. Light falls into that, and it's grated to different range, and that's what the color you are able to see here. So there are many grating systems available, either reflecting or transmitting grating systems. So your light falls on this. You have a focusing lens, you have a collimating lens, you have a camera lens. Finally, the data, the grating gets into spread up like this. So this is what the transmission grating, and one is the reflecting grating, where the light reflects back and get grated. And so these are the two kind of grating system what you have. You have also, in many sensors, you have a concave grating, and you have also convex grating. This is what in the different sensors we have different grating systems. And there are also many filters what people use: liquid crystal tunable filter and acoustic optical tunable filter. These are different filters which is used in the imaging spectrometers. Again, there are instruments, for example, you might have heard called FTIR, that is nothing but Fourier transform in uh, infrared spectroscopy. So there again, Fourier transformation takes place with respect to the movement in the there is one fixed mirror, there is one beam which keeps on moving. Based on that, you will be able to get interferometer, and based on that you will be able to get the signals. So these are different systems, the sensor systems, getting prisms and FTR and also filter sensors, and you can see with respect to their parameter how they behave. And mostly the grating system, most of the sensors we use is a grating system, and they are very highly useful. And coming back to the spectral resolutions, why at all we need to work for hyperspectral? For example, you look at a mineral called kaolite, where you have a multispectral bands like TM. You can see the channels what you have here, and look down here where you have a spectrometer which captures the data. And you can see this is looks like a very smooth curve going without having much interactions, where you have large number of interactions here. So that means there's a unique interaction, because there is a unique at particular features, for example 1.4, 1.9, because of hydroxyl bonds with that mineral which you can identify. So that is the basic behind. If you have a multispectral, you information is very, very less. When you go a little more number of channels, the information getting better, more ups and downs, means more interactions and more features and characterizations. Same also with respect to vegetations. You look at the multispectral on the left hand side, you look at the hyperspectral in the right hand side. In case of multispectral, you have a discrete channels like this, so you can have few bands for that purpose, a few characterizations you can do. When you have a hyperspectral, you have a continuous spectrum, so that in between, if there is an interaction in between, if at all there is something to be captured, you can capture and do. So multispectral will be giving you some informations, not that whole information, whereas in hyperspectral you can think of any parameter, you can able to get it, provided those parameters has a visible impact on the 400 to on those spectral ranges. So you can see the kind of leaf water content or nitrogen and this drop down, which you are not able to see in this case. There is hardly anything here. So you will be missing some of those informations if at all you don't have hyperspectral. And that is the purpose why we have hyperspectral. Coming back to this is again one of our colleague from JPL, Robert Green, who was coordinating our NASA average campaign in country. And he says the life on Earth, photosynthesis, is revealed via spectroscopy. You look at this photosynthesis process, as this is basic school botany when we have been taught. You look at this left hand side and right hand side, each part of these parameters, each component of both sides, you can capture by the spectrometers. You talk of oxygen, you talk of water, talk of carbon dioxide, talk of carbohydrate, every part you can capture. So that's the reason what I'm saying is, so you can characterize whole plant. That's why it's called a PET scanner, hyperspectral remote sensing, because every part of it is taken care. So coming back to the sensor platforms, you have and the ground sensors where you can use on the ground some of those instruments. For example, you can see here spectrometers or imaging spectrometers you can use on the ground. We have now drone remote sensing where you can put all those sensors on the drone. We can put also manned aerial vehicles like we have average NG we conducted, and also you can put on the satellite. So this is the different level of platforms where all these spectrometers are available. You can see, for example, this is what the facility we have. So you can have the lab conditions, the soil capture. Same instrument you can take to the field conditions. You can put on a cherry picker over here, or you can put on a drone, or you can put on a manned aerial vehicle, or you have in the satellite. So, or you have an elevated platform where you can scan through. So this is what the capability, what you can have with respect to capturing those variabilities from the single pixel to large field scale. Coming back to the story behind sensor technology or space technologies. So initially, 1969, the first remote sensing started again from this campus, from this division where I am too. So NASA, ISRO, IIRE collaborations. The first is detecting coconut wilt disease in Kerala in 1969. And you again, that kind of collaboration you had that time. Again, almost 50 years has passed. Again, recent collaboration with respect to efficiency, and also nicer. We had again ISRO, NASA, again IRE was also part of this science campaign. So we have many places where the data has been captured, and we witnessed the wonderful results what it came through. Again, in 2019, what happened is same place where this is a Kayankulam of the Kerala where coconut wilt was happening. So you can see this is the same patch where you moved, and this is the same building which you can see over here. We went with a drone with a sensor, with a hyperspectral sensor, and capture the data just to commemorate, celebrate 50 years of remote sensing with respect to advancement what we have done with. And you can see this person who is sitting over here. He is Mr. N.G. Pillai, who was on this science camp in 1969. He was too old, but his son was working in that institute. So we got him over here. He shared his experience, how wonderfully the ISRO has moved from the technology in 1970s to 2020s now, having different sensors with a different advancement. So that's what the advancement we have done over the time. And these are the different sensors which is available, spaceborne hyperspectral sensors, and this is what the different airborne sensors. I think many of these are available in the literatures. So this is what the manned aerial vehicle, where you have all these sensors in the different ranges, which is available. Coming back to the genesis of the airborne sensors or the hyperspectral imaging spectrometer, initially in the first 1996, Space Application Center ISRO started a airborne imaging spectrometer with the range starting from 0.4 to 0.8 spectral range. That was the first. You can see the how huge is the this imaging spectrometer which has gone on the manned aerial vehicle. Then later, we started with the airborne HIC, which is you can see over here. This is again something around 0.4 to 0.9. The same airborne HIC has gone also on the Chandrayaan mission. So this is what we have a HIC sensors which has gone on Chandrayaan, and also you have on the nano satellite, it has also gone for terrestrial mapping. This is what I was saying. IMS-1 and Chandrayaan-1, the same HIC sensor has gone with 0.4 to 0.96 nanometer. And you can see here, this is what a Chandrayaan mission, you can see the kind of hyperspectral sensors. There are two sensors has gone, one from NASA called Moon Mineralogy Mapper, one from Hyperspectral Imager from India. This was the first Chandrayaan mission which was conducted. And this is what kind of a spectral library of the signatures of the different rocks and minerals from the moon could be captured using the sensor what we have launched for. And this is what whole moon mineralogy has been done using that M-Cube sensor, Moon Mineral Mapper, what the JPL has launched. And you can see the kind of dominancy of the different minerals in the moon surface, basaltic, pyroxic, and basaltic olivine. So this is what the kind of study which was done. Again, discovery of water on moon, you must have all these things. So this is again done by the sensors which has a absorption something around 2.8, again something around 3.2. This is what water absorption bands. Again, we could see that this is what the possible, because when the there is a sensor, I think moon impact probe, through that only when it entered to moon's surface, close to moon's surface, they could see there are some absorption bands, and these ranges they could find there may be possibility of water. So that's what the invention which has been done. And then we have GSAT-1, where again hyperspectral sensors of a 320 meter resolution Vienna range and SUI range of 192 meter was planned again for every 30-minute interval. Again, in Cartosat 3, this is what the kind of a hyperspectral bands with the 200 bands with the 12 meter resolutions, which was planned. I think one satellite has been launched, which has been gone for the mostly the defense purpose. For civilian, it is yet to be available. So this is again India's planned sense imaging spectrometers, imaging IR spectrometer, which has been under the process for lunar mineralogy for the Chandrayaan-2 mission. And so this is what the Chandrayaan-2 mission for that sensor, again, hyperspectral sensor has been planned for that purpose. You know the MOM mission, Moon Mars Orbiter mission. Again, we have a hyperspectral sensor having 120 channels from 7 to 14 meter ranges. And so these are some of those innovations which we have done. And this is what aqua, atmospheric air sounder, what ISRO has been working for different aerosol chemistry. And this is again a hyperspectral sensors for atmospheric compositions and studies. This is what IC, infrared atmospheric sounding interferometer. So there is a huge number of instruments what we have with us. And this is again another sensors called what is visual infrared thermal imaging spectrometers, where you have a BNR, also MI range with the European Space Agency. And there is also another called Prisma, precursor introspectral della mission, that's again from Italy. So these are some of those sensors which have been still active. Prisma is still active, and you can download those data. So we had the Hyperion, I think, yes. So we have imaging Hyperion sensors, that is a NASA. There we have around something around 242 channels with a good band, something around 158. Again, that was a boon again to many remote sensing community to work on satellite-based hyperspectral remote sensing data acquisition for different applications. This is one of the study which we try to do somewhere in Jalandhar regions for the soil mapping. You can see how the strip looks like, something around 7 kilometer by 110 kilometer. The strip, that's what the swath and the length you can see in one acquisition. And each point you click, you will get a spectra starting from 400 to 2500, and you can go for different applications. So coming back to the ISRO's joining, starting from 1969 to 2018, you can see number of places we have a hyperspectral mission. Also very recent, what we have done is, as I told, AIMS and AIC, and also we have now INSAR campaign and also Average NG campaign. So these are the different campaign which has been taken place at the different places. Come up to 20 minutes. So this is what airborne hyperspectral remote sensing in India, what NRSC has been doing in collaboration with the JPL, NASA, and also Space Application Center was involved with 35 collaborating institutes with different applications related to geology, agriculture, water, forestry, snow, man-made, built-up algorithms and database. So this is what Average NG, what I was talking to you about. Of course, the next generation is there, and this is what the flight on which the instrument goes in. And this is what the whole team of ISRO and science campaign team of India, who are involved in this big campaigning all around the country, capturing the data. You can see the kind of sensor which has gone on our ISRO flight, and different places it has been flown and captures the data. This is what the Robert Green over here, Dr. Bimal Bhattacharya, who was the national coordinator for this campaign, and then whole science team is available here from different thematic applications. So this is what the NASA sensor in the visible near infrared spectroscopy, so which is flown over the King Air base 200 at height something around 3 to 8 kilometer. And the campaign was something around 2016-18. This campaign was done, and this is what the different places we were part of that campaign, and same time also going with a hyperspectral sensor down in the collecting different soil data. So this is what in the different campaign where we have witnessed and we capture all those data in collaboration with the Space Application Center and many ICER and also state agriculture universities. So we have huge database for that purpose to understand how best we can explore this potential of a hyperspectral remote sensing for soil and crop health monitoring. Coming back quickly on the drone remote sensing, recently it's a very buzzword, which is very user friendly, and the government has taken a lot of initiative to make you comfort to get into drone technology into different applications, mostly into agriculture. Again, drone remote sensing plays a very important with respect to agriculture. And forget the multispectral sensor. There are different multispectral sensors are available. Of course, again, there is a hyperspectral sensor which is available. So you can fly through, for example, you have a hyperspectral sensor, which is over here, something around 600 grams, and you can fly and capture the data. You are the hyperspectral sensor flying, and this is what the data is captured, and you can see the spectral signatures before corrections and after corrections, how the spectral signature. Of course, the data range is 400 to 1000 here. We are in the process of getting some more. So The hyperspectral drone remote sensing is nothing but a real-time CAD scanner of the crop or any target you are looking at. You can see this is what the hyperspectral sensor has gone with the drone with a payload carrying something around 7 to 10 kg payload with a gimbal, and you can see that it captures the data, and within no time, if you have a data analytics, then you are able to see with the different color how the water stress is captured, how the normal condition behaves, how the nitrogen stress is captured. So this is what the wonderful um, platforms what you can do it. Coming back to little with the ground remote sensing, these are the different ground sensors which is available. If at all you don't have the airborne or the satellite borne imaging data, always we can work with the any remote sensing work research you want to do. You have to start with a spectrometer so that you can find out what is that sensitive bands for particular purpose or applications you want to work for. So this is the minimum requirement for any hyperspectral remote sensing you want to do. And this is what the lab, which is a dark studio kind of thing, no outside light condition will be there, so that you can start working on that. And this is what the spectral signatures you get. And this is again a MR observance which beyond to 2500 you can collect the spectral signatures. You can see the kind of chemicals what you can the composition you can capture. This is again a emissivity based instrument called FTF D&P from US, which was again taken, and you can see the kind of emissivity spectra, which is the intrinsic property of the target, and based on that one can characterize. Of course, this is average energy spectra. So you have a ground spectral ranges and you have a airborne spectral ranges also from the satellite. How best you can characterize the feature, that is what most important is. Coming back to some of the sensors which were on the control conditions, you can see, so we have the facility where we call high throughput plant phenomics facility is kind of a sophisticated hospital where you have all kind of imaging possible and you can diagnose what are happening to the plant. So you have two hyperspectral sensors which captures the data, and once the plant goes there and captures the data, you can characterize how the plant is behaving with respect to other plant or with respect to interaction with the nitrogen or water or pest or disease, anything. And we have also drones where we can try the same sensor and do it, and or you have a robot where you can integrate that and go through. So these are all possible applications. I think I should skip. Coming back to the spectrometer, this is what already I told about all, and this is what the spectral data you generate. I think this is what the observance spectra you generate, and based on that you can see the kind of interactions what takes place, and based on that you can find out what are those amide groups or CH groups or OH groups. You can identify. Based on that you can characterize what kind of soil it is, and you can pull them together. So you have a reflectance starting from 400 to 16,400 nanometer. You have a whole spectrum to go for modeling or characterizing the data. So you don't have any sensor which gives starting from 400 to 16,000. So you have two sensors. We try to put them together and characterize whole range, how better you can characterize. This is what emissivity spectra, this is what that instrument which can work again in the emissivity range, and this is what the ranges you are able to get it. So when you go for inter-comparisons, starting from the lab conditions, like you have a spectrometer which is with the touch with the target. So you get a spectrum like this, blue spectrum, and you same sensor you take to the sunlight conditions. This is a red spectra what you get. When you go to the field conditions, you get the black spectra like this. When you go to the satellite level Hyperion, you get a lot of noises here. So whatever the study you do, you want to do in a single pixel level to the field scale. So this is what one has to go for uh, when you want to scale up, you should go for evaluations, how best whatever the model I have developed, how best is going to work in the lab conditions and how best I can take up with the field conditions. And those blue bars are nothing but the atmospheric noise channels. So those parts has to be removed. And you can see the kind of a comparison again that you have a ground sensor. For example, ASD is the ground spectrometer. Average is the airborne, that's what the spectral signatures. And this is what the satellite based signatures. So you can see the kind of a comparisons, how it behaves, what the response you get. So, so the signal noise ratio and also the number of the interaction with the atmosphere, it matters how you are taking the data and what platform you are taking. So this is what the different data sets, and you need to go for different kind of processing because a lot of noises you have, and then you have different molding approaches, and to find out some of the sensitive bands because you have a huge number of channels to find out some of those sensitive bands for your particular purpose, for a soil or for crop or for geology or for any purpose to develop a low cost sensor. There is again, these are the techniques which can be used to find out those sensitive bands for that purpose. For example, I have done a comparative evaluations starting from the ground spectrometer with the average NG, with the observance, with the emissivity, again the whole range combining. You are able to see the which instrument is really working good with respect to the soil parameter estimations. So this is what the MI spectroscopy looks to be better. So this is what kind of evaluations one can do, and you can go for the complementing some of those national programs for the soil health or crop insurance or anything. How these sensors, for example, hyperspectral, I'll come back to the vegetations. So how these sensors can be useful with respect to damage assessment, with respect to decomposing or discerning different composite stresses, what you have in a field conditions. So this is again the kind of a scalable from the lab to the field to the satellite level. You can see the prediction model, how it works. So when you have a lab conditions, you have a wonderful data, prediction model is good. When you go to field, again goes down. When you go to the satellite level, it has gone down. So this is what the kind of study needs to be done to understand what are the limitations, challenges, or opportunity we have. So coming back to the average NG, what we try to do, we use those opportunity what we had with respect to science campaign, and we have a last spectra, and we have same time also airborne spectra. Based on that, we try to come out with the kind of a regional scale different soil fertility parameter. One example I am giving here is available nitrogen, and these dot points, yellow dot points, are the field where we collected the samples and gone with the instrument to capture the ground spectral data. So this is what the process. But onto this, there are a lot of machine learning, deep learning program as the algorithm has gone in for processing and come out with this product like this. So you have a raw data, and from the raw data, you got an organic carbon mapping, which is very useful. Again, in between, you have a lot of process what one has to do for. Then coming back to the UAV-based hyperspectral, this is what the sensor, and this is what the spectra you try to get. And based on that, you can characterize different parameters. For example, you look at, we try to evaluate different sensors starting from multispectral, RGB, and hyperspectral. So RGB, you have only 3 channels, whereas multispectral, you have only 5 channels you have. Whereas in the case of hyperspectral, you have so many channels. For example, you can see here. So how wonderfully this, when you go for the evaluations, you can see what are the limitations with respect to multispectral, what are the advantages about the hyperspectral. So those kind of studies has been carried out, and this is what the spectral signatures you try to see, and this is what the prediction model you are able to get with respect to nitrogen, and this is what the spectral signatures you are getting on those ranges. So when you do with the multispectral, this is what the kind of data. When you do with the hyperspectral, this is what the nitrogen content map you are able to see. This is again a prediction model developed from the hyperspectral. So again, there is an advanced science with respect to BRDF, particular directional measurements. So there are facilities called goniometer where you can put these sensors, spectra, hyperspectral sensors. You look at the same soil, but the signature is varying. You can see because the directional effect is there. So again, look at the same crop, same time, but there is a spectral signature is changing. So that matters a lot. So this is what the directional property of the target or the sensor with respect to the source. One has to study that. So based on that, you can characterize the target much better way with respect to relative position of the sun and zenith. Again, this is one kind of advanced studies, what one has to do. So I think I should skip this. So coming back to the data analytics. So I talked about the sensor, I talked about the platforms. Now coming back to the data analytics. It's a huge data. So this is what the common processor step you use. Raw data, you go for radiometric corrections as you have. Then you should have a geometric corrections. Radiometric corrections using the reference panel, what you have with respect to optimization of the light conditions. You should have a geometric corrections. Then you have atmospheric corrections because a lot of interaction takes place. And of course, you have to remove some of those noise informations. Also, you have a huge data, so it's going to be huge noise for you also many times. More information, sometimes noise. Then you go for information extraction. So this is what the step usually followed, and it's a huge processing. And as I told, common image processing software like whatever you have with respect to Eredas or Idrishi or Envy, you need to have a special model for this atmospheric corrections or hyperspectral data analytics. So, for example, we use FLAS, we use ATCA for those purposes for atmospheric corrections. So, I say hyperspectral remote sensing is a big data. As I told you, it's in GBs because it's a huge single pixel having large number of channels starting from 0.4 to 2.5. So it's a huge data, and it qualifies all the character of a big data. So you look at the digital number to radiance conversion, spectral spatial processing. So this is what the kind of challenges what you have, and radiance to reflectance conversion, then data volume or redundancy what you have. So these are the processes what one has to do. Then one has to go for spectral matching, how you can do using the bandwidth analysis or continuous removal or positioning, strength and shape of the observation features. So some of the challenges what we have with respect to data analytics is you can see here: data archive and distributions, tackling that low signal noise ratio, atmospheric corrections, interpreting spectral signature of a impure pixel, because sometimes the resolution is, for example, 30 meter, 10 meter. Within that, there will be number of other features also. So this is what the challenge you have. So how to characterize on mixing we can do. So these are some of the challenges what you have. I think subsequent speakers, they are going to talk all about that: data processing, spectral library for the soil, crop, rocks, minerals, then calibration and validations, then combining and different sensors in different ranges, how we can uh, bring down to sensor calibration so that we can evaluate them. So these are different algorithms what can be used for hyperspectral data analytics. So there are many already people have been working with. So these are some of those challenges I can say. So you need to have a spectral library of Earth surface features, local, regional, and global scale, and you should have a good understanding on physical, chemical, biological properties of the target and characterizations. So using this hyperspectral one can do. So you can do monitoring, mapping, and discrimination and quantitative analysis also. You can generate thematic products, and you have understanding of different ecological processes. So this is what the hyperspectral opportunities and challenges already I told. The challenges are many approaches, tools, and applications. So there are huge available with us also in the 37 institute they have been working. So you need to standardize them, make it a generic, local to regional studies. When you want to do need a larger scale, then you need to really generalize, make a generic model for that. And application demand for the new ecosystem products, like you need to develop a LI product, NPP product, or water stress product, or nitrogen product. So one has to do those kind of studies for that purpose. I think I can skip all those things. These are different applications I think people are going to talk about. So forestry, huge application it has. So if you want to talk about that, I think you need a days together to talk all about that. So geology applications for different mineral explorations, and also for the snow applications, huge applications have been done by SASE. Now it's a GDRE in the Chandigarh. They have been working on snow avalanche studies. We had also a huge dedicated team for each theme what I am talking. Water studies, water quality, water turbidity, and also many algals, booms, and chlorophyll and phytoplanktons, all those studies. Of course, it has a many. I started with the DST, the program on the particularly from the defense purpose with respect to camouflaging. That's what my past project was with respect to hyperspectral, and also identifying composite minerals, built up areas, bridges, roads, runways, and also bathymetric analysis, strategic target detections, bathymetric because of the turbidity and water spectroscopy, then trafficability, soil constituents, how we can do it. So this is what some initiatives from the DST which was taken with us, and a lot of advancement already done. I think if I talk of 2016, now 2022, I think we have something around 100 plus PhD students passed out from the 37 institutes, and huge capacity building has been done thanks to DST team who supported this program. And we have a huge application. We developed our own software for that purpose also. I think it's going to be available for many purposes. I think again the major issue with respect to applications, like the audience, the participant over here, you have most of the studies what you have satellite based UN, Hyperion, or anything, they're all archived. And so you don't have anything which you can play with except average NG and some of those satellites which is archived, and real time you can't do. Again, anything you want to do on the proximal remote sensing, so you have that instrument called spectrometer, which is very expensive. So and again, proximal thermal hyperspectral is again highly expensive and not explored much. And if at all somebody has to work, so you need to buy those. So that's the reason you have very few ground or airborne imaging spectrometers or satellite-borne data. So we need to build up that capability with us and the community. I think this is one of the opportunity what Dr. Rosan has taken initiative, built up the capacity to play with those data which is already available, so that with the funding we can get some of those instruments and try to work with. So this is what the future thrusts to be prospective plan for India for imaging spectrometer, airborne and satellite platforms. Of course, since I told you airborne, already many people started working on that. And then modality to avail airborne HS data as per the need of researchers. Of course, that has been a success now, and we got a lot of data with respect to average NG. And collaborative effort with the different agencies together with respect to optical, thermal range, and also application domain exports. If you can put us together, technology exports, computer science export, the data analytics exports, data science team, and the thematic domain exports, they are together, then I think can address some of those areas what I am talking. This is what the recent program we have taken up again a big way in the 16 research institutes, where hyperspectral is going to be a key issue or key role for that purpose. I think I must thank to each and everyone for patience hearing. And I have, I think, maybe around 7 minutes. I have 7 to 8 minutes just to, if at all there is any question, to interact. This is what the post-harvest solutions you can do. For example, any fruits you see, their signatures, how they're different. So you can segregate them. Not only that, you can differentiate also basmati, non-basmati, aromatic, non-aromatic. So that's what the capability of hyperspectral. So thank you very much.
Sir, are you able to hear us?
Yes, I am.
Is there any questions from the attendees?
Somebody is asking, can you share this PPT? I'll convert that to PDF and share with Professor Roshan. It will be available to you.
What we're going to do is we are going to collect the PPTs from the expert. We'll put it in a folder and share it with the participants all together. I think you should be having a lot of questions because he's one of the pioneers in hyperspectral imagery. So is there one question has come? Is there any development in classifying the rice using a mobile app using hyperspectral imaging?
My answer is yes.
So your voice is not coming.
Oh, is audible? I'm
Yeah,
audible.
it's there.
So my answer is yes, because of the limitations of time. I didn't show you the applications. We have something around 132 genotypes. We have discriminated them using hyperspectral. We have 10,000 land races of rice grown in pan India, whatever grown in one field. We have grown something around 500 by 500 meter. We had an airborne campaign, and where you could see their discrimination. It is possible, but to do in a multispectral is not. And again, using mobile app is a challenge, because the mobile app hyperspectral data analytics is going to be difficult because it's huge data.
So there's
Hyperspectral is a huge issue. Is there any way so that students can also access it easily? That's what I was saying, Bashudha. So there is a site and where you can log in for average NG data, which is available by this science campaign, which has been done with the ISRO. So you can Google and see that. Otherwise, I'll share the link with the Roshan to see if at all those archive data can be available. That is one. Or you can log into average NG site to get that. And also there is Others like Hyperion data, also archive data, you always can download of your interest area, but it is old data. You always can play with that. Another question is, as of now, this technology is primarily used by the government and research organizations. If, for example, a farmer wants to use this technology for a standalone case, how should they go about it? Not possible. For farmer, it is not possible because, like, for example, for farmer, you need to pack it and make it very simple and understandable. So you, if at all on a mobile or in a drone, you have a hyperspectral is flowing, within no time you are able to identify the diseases and you can go for recommend you should go for spraying. So farmer is not going to fly the drone with the hyperspectral, but there will be a agriculture graduate or pure or a KVK who can fly that. And we have 300 KV drones given to 300 KVKs now. So that is the purpose, so that you can fly with the sensor, can have the data analytics to identify what happening. Then you can recommend what farmer is supposed to do. But an educated farmer can do this business. For example, you have a tractor you can use for multi-purpose. You can even rent Uber like Uberization you do. Same also in case of you can have a airborne hyperspectral, and but it's a very rich. You can think of you have to spend 100 lakhs, so you should get the business out of it. So, but of course, you can do that provided you develop all those possible applications or algos to identify some of those parameters, as I said. But for common man, it is not. Welcome. Somebody has said.
There is one more question. I'm interested to avail the archived Hyperion data of Odisha. What steps I need to follow, sir?
I have data I can share with you. You just write a mail to me. Otherwise, there is a link where you can avail it. Yeah.
So the
Best
next
source of
question.
what is the best source of different RISE signatures, sir? And what is the source for HSI? Is it possible to get HIS data using average NG from different locations as we need? Please share some light. RISE signatures, we have created a huge signatures of different RISE with the different treatment with respect to nitrogen and water. Have that. Again, coming back to the average NG, there is a BEDAS site of Space Application Center and also NASA site. You can register there and you can put a request. You can get the data to play with. I think my mail ID already I have given on the presentation, but still let me write down this. So this is my personal mail ID, and this is my official mail ID. The chat box, it is there. So
Yeah. Shall we contact you for further information or clarification, sir?
shall we contact you for? Yeah, sure.
We have actually put up all the email IDs in the browser itself. Any expert you want to get connected, the email IDs are already available.
Okay.
Sir, I have one question.
Yes, Roshan.
So, where do you see hyperspectral remote sensing in next 5 years? What do you think we should focus as a researcher, as a product development for the market? Which sector which should you think like we should be focusing if I would like to make a startup tomorrow?
You should look at doing business out of it. Then you should look at the like quality grading of the produces. The produce may be the cereals like rice, wheat, or anything. Produce may be the fruits, maybe apple or mango or something. Or produce may be the meat. How good quality is the meat? That is one aspect. Second aspect is hyperspectral is able to, in a regional scale, suppose you have a drone and you want to fly with. So within no time, we should be able to know how much is the nitrogen deficit, or if there is a disease or there is a water stress. That stresses you can discern, and you will be able to develop a management options for that purpose. So you want to do a smart farming in an area like you have a tea garden, you have a coffee garden, you want to do those kind of studies to identify and go for the smart farming with respect to input management. Again, hyperspectral helps. Again, you can do in case of quality monitoring with respect to the tea or with respect to coffee. Then again, this kind of studies is very much helpful. There are many other applications. For example, you have built up a road. How good quality is the road? That can be done also. The tire characterization can be done also, and also the paint. You have a heritage, like in the DST there was a program. So you want to characterize that. How good is that paint, or what was the chemical compositions, and how good it is? Those kind of characterization can be done. And so there are many applications one can look at for that purpose.
Thank you, sir. Is there any other questions from the attendees?
I don't think any question. I think I must thank to
There's
you.
one more, sir. There's one more. Professor, is there any source for the forest tree species spectral library? If so, can you please share the source?
So we had a team of forestry led by the university, and the PI was Mr. Dr. Professor Krishnaya. So we developed some libraries of different forest species. One, and there is also another institute called CSR Institute at IHBT. That's called IHBT. There is one PI called Amit Kumar. They have been working on spectral library for forestries. So they may be contacted for sharing or maybe collaboration for that purpose. And forest monitoring, there are a lot. One is your mortality with respect to disease, aging, with respect to at what age the plants are, and most importantly is the discrimination. Like you have always a forest has a different composition of species, so you can discriminate them. You can characterize them much better way because they are going to be nature, so is going to be different. Again, with respect to carbon sequestration, how much liter, and all those studies, it can be done. Mortality with respect to pest and disease, that can be done. You can do drought analysis using multispectral. So why at all you need to go for hyperspectral? So the drought is going to be easy for you to do with multispectral. You have many sensitive water bands, thermally more sensitive you can use. So you can do with the multispectral, not necessary to go for hyperspectral. Can you avail spectrometer facility from any institute? Yes, you can avail, but I think there is a payment basis you can do. For example, my institute charges something around 1,000 per spectra to be collected and shared with anybody, and so that has to be, and there is a pro forma was to be given, and data can be generated and shared with you.
Okay. Sir, I think thank you. Thanks a lot. I think it was wonderful to have you again hearing, and with the same passion what I've been hearing last time, you've been putting it. I think a lot of attendees might have learned a lot about the introduction on hyperspectral, which also gives us a motivation for me, at least our team here was always happy to see the way hyperspectral imagery is growing and the way you put up in different sectors for us. Thank you again, sir. Thank you for uh, architecting, creating this workshop in a way it is now. Thank you for joining us as a guest and also as a speaker. Thank you again, sir.
Thank you. Thank you all.
Thank you.
Thank you.
Okay, I request all the attendees to stay back at 11:45. We are going to have the next session starting.
So Roshan, I'll be joining, but I'll be passive. I
No
would
problems.
like to listen to others. So, but I won't be
Sure,
active.
sure.
Okay.
No, no problems.
Thank you. Thank you.
Yeah, thank you, sir. Thanks a lot.
Bye.
There is a slight delay of about 5 minutes. So we are just getting connected with the speaker. I appreciate your patience. Please be online. Very soon we are going to start the lecture. Thank you.
Suppose I have only particular wavelength range, then if you have 10 band and we are using only red wavelength region, then that also comes under hyperspectral. So here, please remember when we are considering full wavelength region visible to reflected infrared, then you have no number of spectral bands. So here, because of lot of spectral information, we can actually identify and distinguish spectrally similar wavelengths. So these are few of the sensors that is airborne. So recently we ISRO and NASA have collaboration, and the data was acquired for various Indian sites. So the data sets are available. If you want, you can work. This is with an airborne platform with a very high spatial resolution data. Recently launched sensor. So here you can see Hyperion sensor was one of the sensors which was launched in 2000, and it was just following Landsat 780, Landsat 7 satellite, 1 minute behind. Chris sensor was one Proba 1 satellite, which is having multi-viewing capability. They can acquire data with a multi-viewing capability so that you can use it for different kind of applications. Then HISIS was launched from ISRO recently in 2018, and Prisma was launched in 2019 from Italian Space Agency. HISIS sensor was actually for the defense purpose, so civilians are not using it. Prisma was launched by Italian Space Agency with 30-meter spatial resolution, and INMAP is launched from German Space Agency recently, means this year. And coming to spectroradiometer is one of the ground-based spectroradiometer. And these are few of the another hyperspectral method. HISP is going to be launched from NASA. GISAT is from ISRO. And Hypersat was, you can say, as commercial constellation of 6 high-resolution hyperspectral satellites. This is the example of Avery's NG image for Buxar area where we have Ganga River. And you can see in this case, we have 425 spectral bands, 5 nanometer spectral resolution, spectral resolution. Here you can see when clear water is there, spectral reflectance curve is comparatively less with compared to your ground spectra. And here you can see there is a drainage of opening. So because of that, turbidity of water got increased. Because of that sediments, you can see the reflectance of water got increased. So this is the difference with clear water and water which is with some contaminants. So how the reflectance curve is changing, and it is comparable with your ground-based method. This was your Hyperion data. So some of the processing thing which I have performed that I'll be showing through this data. This is from Rishikesh area data, which is with normally inherent capability for this is 220 spectral bands with 400 to 2500 nanometer spectral resolution, 30 meter spatial, and here you can see 7.5 kilometer is the swath width. So swath width you can see if you will compare with Landsat satellites, normally they are with 185 kilometer swath width. It is with 7.5 kilometers. This is your HISIS sensor specification with VNIR sensor ranging from 400 to 950 nanometer and with 16 VNIR bands and 850 to 2500 nanometer with 256 bands. So you can see there are overlap between the two ranges. But normally what happens is for different sensors, the detectors for VNIR and SWIR are different. So that's why they have little overlap in between. Now coming to if suppose we don't have hyperspectral sensor, then what we can do? So we have done one of the research. To what we can do is we can simulate hyperspectral bands from multispectral data. So we have used here ALI data, which was on the same platform EO1 satellite, and we have used Hyperion data for validation. So we use ground spectra and we use multispectral data. We simulated around 70 spectral bands. And when we compare this 70 spectral bands, you can see the spectral reflectance profile is coming more or less similar. So we have developed the software for this, for simulating the data. And if the data sets are not available, we have multispectral data. We can simulate hyperspectral data along with some ground data. So here the correlation between the bands we observed was most of the bands shows more than 80% correlation, and maximum of the bands have shown 90% correlation. So coming to the data quality, normally, when there is a spatial noise, it hampers the visual interpretation. But if the spectral noise will happen, so the important thing in hyperspectral is what? Absorption feature. So when the absorption feature is getting affected, then you will not be able to do the statistical calculation properly. You cannot match the spectral absorption with your reference spectral profile. So if the depth and shape will not match, you will not be able to classify the features. And the sources of noise is what? Sensor drift. Like whenever you are launching any sensor, it will work with full efficiency. But after some years of use, it will deteriorate with time. So it will work, but it will include certain kind of noise. Coming to another source of noise is signal conversion. Whenever we are doing analog to digital conversion, then also noise is including in electronic vibrations and moving parts in the sensor can cause platform vibrations, especially aircraft engines, that also can cause due to your atmosphere, like when irradiation variation will happen, like due to your different weather condition, like summer and winter you acquire, during morning and noon you acquire, your solar variation can cause the some kind of error or noise in the data. Then atmospheric attenuation, like scattering absorption happens, atmospheric path radiance because of multiple scattering. So this type of things which are causing the errors. How to reduce that kind of noises? So first I'll be talking about the sensor noises. So here, whenever you will download the data of Hyperion sensor, so here you can see total 242 bands normally you will be getting, but the inherent capability is 220. So there are overlapping bands between VNIR and switch, so that needs to be discarded. And whenever you see the data, some of the bands will contain no information. So these are your actually water absorption bands or atmospheric absorption bands. So this you have to remove. These bands are of no use. And as I told to you that because of sensor error, you can see that somehow stripping error or drop line error will come. So what you have to do is first either you remove the bad bands, and removing the bad columns, if you have to do, then what you have to do, you have to run low pass or beam filter to entire data, so that you can take the averaging out of those pixels. Because these are, suppose this drop line happened, and we don't know the information that what actually happened. So we have to apply cosmetic correction, and nearest neighbor pixels are somehow more or less similar. So take the average of that and remove that entire pixel in the image. And third way is to reduce the noise for is one of the technique that is called as minimum noise fraction, which I'll be discussing in my data dimensionality reduction, that how it is reducing. And along with the noise reduction, it also does do the data dimensionality reduction. So this is your entire hyperspectral data processing. Normally, whenever you will download any hyperspectral data, the data sets will be in the radiance form, and you have to convert to surface reflectance by performing atmospheric correction. As I told that there are various things which are playing a role for introducing the noise, atmospheric error. So this needs to be converted to surface reflectance. Once you convert to surface reflectance, you have to go for the data dimensionality reduction. And in the process of data dimensionality reduction, you can extract the end member extraction after that. Because one of the essential steps for end member extraction is data dimensionality reduction. Or when you have a spectral library, you can use the spectral library to classify the data. And you can use the same spectral library to identify the particular materials of the features. So So these are few of the atmospheric correction approaches. One is empirical approach, another is absolute approach. Empirical approach is what, when you have somehow you can say, let me say I have given you an image and I don't know any parameter to correct the data. Then what to do? So we have to use image based method where we have to find out, like suppose in an image you have a flat. Take the particular flat field, take the average pixel value of flat field. And normally to convert the data to reflectance, we require two measurements, radiance and irradiance. And ratio of radiance and irradiance is reflectance. So here you somehow think that data is in radiance. You take the average pixel value of some bare field. Bare field is normally highly reflective object. So take the average pixel value of that, divide from each and every pixel, that is your flat field correction. Second correction is IARR, that is internal average relative reflectance. So in this case, what we are doing is we are considering whole image as your data. Take the average pixel value of whole image, but one condition is that in that case, the data should have no vegetation. Then only it will work better. So take the average pixel value of entire image, divide from each and every pixel. It will give you the corrected data. Third method is what? In third method, you require ground measurements also. So here what you have to do is you have to solve a linear equation, that is y is equal to ax plus b. So here you can see, suppose this is your image and this is dark object, this is bright object. We went to the ground, we collected the reflectance of dark object, reflectance of bright object. So in the linear equation, y is equal to ax plus b. So here y dark and x dark you have to substitute. Y bright, x bright you have to substitute. Solve these two equations, you will be able to calculate a and b. These constants you will have to calculate. Once you will calculate this constant, you have to take y is equal to x plus b again. A and b now you have calculated, substitute here in that equation. And in place of x, place your entire image, it will give you the relative reflectance data. So this is your empirical approach. Now coming to the absolute approach, in this absolute approach, what we have to do is we have to use radiative transfer model for converting it to surface reflectance. And here, you require various parameters as if like atmospheric condition, water vapor condition, aerosol label, scene sensor geometry, and the data time of acquisition. What is the position information? By knowing all these parameters, then you can convert that to surface reflectance. So these are different models in different softwares. So Flash is placed in fast line of analysis of spectral hypercubes, that is in the NV software. Atrem is in some of the I don't remember the software name, but this is atmospheric removal. And ATCOR is established with ADAS imaging software. In this also there are two models, ATCOR 2 and 3. ATCOR 2 works in the flat area, but our surface is not flat. So whenever you are considering one of the additional parameters, that is DEM, and that in using for converting it to surface reflectance, then ATCOR 3 is being used. So this is how to convert the surface reflectance. So this is after using the flash correction, which is based on Morton 4 radiative transfer model. And after converting it, you can see the nature of your urban features, that how it is coming. This is also for the reflectance conversion using the flash model. So here these are the reflectance radiance profile. This is the surface reflectance profile of vegetation species, dry riverbed, and water. So how the reflectance is converted, which you can use it further for identification of the materials. After that, what you need to do is, after converting it to surface reflectance, if the data is not geometrically corrected, because many times we have to use the radiance level data without geometric error correction. Reason behind that is, if you see this image, in this case drop line is there. Once it will be geometrically corrected, what will happen? It will appear inclined. So averaging of the pixel will not be possible at that time. So that's why it needs to be corrected before doing the geometric correction. So here you can see this is your raw hyperspectral image. And if there is a variation in the location error, you can see in this case, the location should be what and what is happening. So this is the shift in the location which is happening when the data acquisition takes place. Even because of the undulation, the pixel size is also coming different for the same image. So what you have to do, the first thing what we can perform is you can do the geo-corrected. Geo-corrected means you can provide the latitude, longitude information, and GPS aircraft altitude correction you can perform. But your Earth surface is not flat; it is undulated. So whenever we are using DEM as also one of the parameter, and we are generating ortho-rectified image considering GPS, aircraft altitude, and topography, then it will give you the ortho-rectified perspective. So this needs to be done before giving it to user for further analysis. Once you have converted the data to your properly geometrically corrected data, reflectance data, then we can go for the data dimensionality reduction. So here, why we need to do the data dimensionality reduction? So reason for that is what? Normally what happens is, if we have many number of spectral bands, they are correlated with each other. So we have to avoid the correlation. We have to generate uncorrelated component out of the correlated spectral bands. And we have to reduce the number of bands to number of components. So here it is necessary to subset the spectrum of interest, reduce the computational overhead. Now you think of, we are processing with 400 bands, and we are only processing 20 components which are containing most of the information from 400 bytes. So this will reduce the time of processing also and computation, because whenever you process the 400 bands, it will take lot of time, lot of memory for processing it. So for reducing the computation overhead, we have to do the dimensionality reduction. And it reduces the noise also. So if you remember, I talked about MNF is one of the technique which reduces the noise, and it improves the SNR of the data set. So first I'll be talking about there are three data dimensionality reduction technique majorly being used for hyperspectral data processing. PCA is being used in multispectral data dimensionality reduction also. So in PCA, what is happening is, we are trying to generate the from the spectrally correlated bands to uncorrelated components by increasing the variance of the data in those components, and they are spectrally uncorrelated to each other by translating and rotating the axis as such. It consists of maximum information in the data. So in PCA, normally what we assume that the first component should have most of the information, then second, then third, and followed by the increasing number of components will increase the noise. But what is happening is, in that case, it is not following that same trend. Why? Because whenever we are running the PCA, we are only bothering about the from generating the correlated band to uncorrelated components. But because the data set, when you have narrow spectral bands, it includes noise also. So we are not bothered about the noise content present in the data while running the PCA. So what will happen? You can see in this PCA1 is informative, second, third, fourth, fifth. All of a sudden, noisy component will come. Then seventh is informative, eighth is informative. So somehow in between that noisy component is coming, because we have that by running PCA, we are not bothered about the noise. Then what to do? How to get those kind of data which will be following the similar trend with the first component is informative to increasing number of component, noise will increase. So in that case, what we are doing is we are running MNF. MNF, the name itself says minimum noise fraction. So minimum noise fraction components is how it is working. In this case, we are applying PCA twice. First, to reduce the noise component, and second, to generate uncorrelated component from the noise reduced data. So how it is being done? In this case, we are using a shift difference method. Normally, what happens in the data is, normally nearest neighbor pixels will have similar values, but the amount of noise will vary. So what will happen? Nearest neighbor pixels. So we are using image differencing method by shift difference method by differencing from neighboring pixels, and we are calculating the noise amount present in the data. So while doing that, you can see here that first component is informative, second, third, fourth, fifth, and as you go towards a higher number of components, noise content will start coming into picture. So this indicates whichever is having high SNR values, will have, which is that will be your first component, then second, then third, and then fourth. As we move towards higher, so degradation of the signal will happen with the increasing number of components. Now you can see why we are using the MNF component for the data. You can see this is your reflectance data. When we use the reflectance data, you can see some of the particular data here. This is red soil and black soil for equisat area. So in this area, it is misclassified. So when we used MNF component, this is misclassification was avoided, and only red soil and black soil classified properly. So this is the difference when you are going to use the MNF components for the data. Then coming to the third data dimensionality reduction. So normally PC and MNF are based on second order derivative, but some of the features have very narrow absorptions. So to identify that second order derivatives are not helpful. So in that case, we are using higher order derivatives like skewness and kurtosis to identify the particular material. So normally independent component analysis, in a simple example, I will try to explain. Like you are standing in a crowded place and somebody known to you is calling, then what will be happening is in that noisy place, you are able to segregate that particular sound or something like you are listening to music. Whenever you listen to the music, you are carefully you when you listen to the music carefully, you will be able to separate out the sound coming from different musical instruments. So that can happen. So similar kind of thing is happening here. In this case, individual signals are getting separated, and here it is highlighting the individual features. Here you can see this kind of feature is highlighted. Here this is highlighted. This are so individual classes are getting separated in this independent component. So now coming to the end member extraction. So end member extraction we can do by the three ways, you can say. From the feed, you can create your own field or lab measurements. So here there is a spectroradiometer. Using that, you can create your own library. You can use that. Second is from the spectral library, which are already available. Some space laboratories have developed, prepared that. It is available in NV software. Estes Spectral is also available on the internet. That also can be used. So these are the spectral library which are available, which can be used. Then coming to the image-based method. In image-based method, first step is minimum noise fraction. So here the data is noise reduced. So these components can be used. Then after we have to run PPI. PPI is actually pixel purity index. This actually identify the most spectrally pure pixel location from the data. And whatever pure pixels you have identified, you have to put into the ND visualizer to extract the. So first I'm talking about spectral data collection by spectroradiometer, how we have to collect, what are the criteria for collecting the data. So normally spectroradiometer should be warm enough before taking any measurement. So it is recommended to start the instrument half an hour before. The battery of spectroradiometer and displaying unit should be fully charged before using that instrument, because you are taking to the field that if the instrument is not charged properly, you will not be able to use for a longer duration. And procedure for spectral data collection is one. So here you can see this is a spectroradiometer connected with a laptop or palm top, you can say. This is your control device which is controlling the instrument, and you can say display device where you are seeing the software and seeing what measurement you are taking. This particular crystal is also connected with this spectroradiometer, and this is a white reference plate. So normally to measure the reflectance curve, we require two measurements, radiance and irradiance. So getting irradiance, for that you have another separate kind of instrument. If that is not available, we can use some kind of material which is highly reflective, or you can say 100% reflective, invisible to reflected infrared wavelength. And this is made up of polytetrafluoroethylene and synchrotron. This is also called as spectral. And here, this is your target. So first, what we have to do is dark current measurement we have to do. What is dark current? Dark current is actually whenever you are not using any electronic device, still some electric current is flowing inside it. So it will be added to the measurement. So first we have to do the dark current measurement. Then after we have to do the white reference measurement. After taking the white reference measurement, you have to go for the target. So this kind of spectral library will be created from this instrument. And here you are seeing a lot of noise in 1400, 1900 and 2500 nanometer. These are your atmospheric absorption. So now coming to the image mesh method. So first step, as I told, where pixel purity index you have to run. So in this case, pixel purity index, what is happening is you have to identify most spectrally pure pixel location in the entire image. So after identifying that, so you can see in this area, these are your mixed pixel. This black is indicating mixed pixel, and bright is indicating the you can say the particular pixel which are pure, and they will have separate numbers, range of numbers for different classes. And here in this ND visualizer, you have two options: ND control and ND visualizer. So ND control is what actually by classification in multispectral data, we are using feature space. Feature space is required, and feature space is band to band feature space we are generating scatter plot. And wherever the pure features will be there, they will be appearing at the extreme. Like you just compare with red and near infrared band. In red and near infrared band, what is happening? If your vegetation features are there, they will have high reflectance and near infrared and low in red. So it will appear at some position. It will have very low in zero in near infrared and very low in red. So it will appear at the other position. So these two are appearing at the extreme positions. So these are this needs to be extracted. So here in this case, we are using 15 MNF components, and whatever pure pixels we have extracted, we have put in the scatter plot, and this is indicating the axis. You have to rotate this axis, and you have to extract whichever pixels are coming at the extreme as sum of the class. So pure pixels occur at the vertices of the geometric figure. That's why it is called as end member. And mixture occurs either along the edges or on one of the faces or in the interior of the geometric figure. So here, these are the extreme pixels which are pure. Whichever are coming in between that, they are your mixed pixels. Now coming to the end member extraction, here you can see by taking that, moving this ND visualizer using this ND control, and we have extracted almost 6 classes in this case, which are existing in these locations. So you can see it here for water, for scrubs, for grassland, for sal vegetation, for urban area, dry river bed. So these classes we have extracted, and by extracting these classes, we can use it for further classes. So this was earlier method was your manual method. Now what we can do is we can use automated techniques for end member extraction. So there are automated techniques which is considering, like suppose one of the technique I'll be explaining is sequential maximum angle convection. So in the code, what is happening? Whatever end members are there, they will be floated, and whichever will be brightest and at the extreme of the cone, that you need to be extracted. So this extreme pixel, so again and again by reiterating, so whatever the pixels which are coming, means first bright you have extracted, then next bright. So by that way you have to extract the end member. So that is your automated technique, and using that we have identified the abundance image, mineral abundance image in the Mars, their hyperspectral data. This is in the Udaipur mines. Urban features, vegetation, phyllite mineral we have highlighted in this. Now coming to the classification of hyperspectral data. So, there are various techniques. 2 techniques are per pixel, and these 2 techniques are your subpixel classification technique, or you can say spectral unmixing techniques. In case of spectral angle mapper classification, normally this is your spectral similarity measure technique, where algorithms are selected based on the characteristics of the image and training data. So here you can see, so normally this particular technique has one of the advantage, because the spectra which you have to classify and the different spectra is there, so they will be plotted in form of vector. And here vector direction is playing role in place of the magnitude. So here you can see, suppose this is your reference spectra, this is the target spectra which we have to classify. So, like for example, I'll give, suppose there is some feature, this is the hidden area, and this area is illuminated, this area is shaded. Okay, same feature is there. This will have different reflectance value. This will have, means you can say higher magnitude in this case, and in this case it will have lower magnitude. So what will happen? The lower magnitude will have this. Suppose in this position it is appearing, and higher magnitude it is appearing in this position. But whatever magnitude it will have, it will, whichever will have minimum angle, it will go to that. So, I'll give you example of minimum to mean distance classifier. Normally, in minimum to mean distance classifier, what we are doing is we are calculating the mean of trailing signature, and whatever pixel we have to classify, we are calculating Euclidean distance. Whichever will have minimum distance, it will go to that. So, in this case, in place of distance, here we are using angle. Minimum the angle, better is the match. And it is insensitive to illumination variation. If there is a variation in the illumination, it will go to the same class. So here this is your spectral angle mapper classification, and this is your maximum likelihood. So because of maximum likelihood classification, you can see many pixels are getting unclassified or misclassified. Now, whenever you do the perform the classification, you are going to generate two types of output: spectral angle mapper and spectral angle mapper classification. Can you just hold on for a minute, because somebody is doing something? I'll just have to put stop. Just 1 second. Sorry for the interruption. Actually, somebody was repairing something outside. So now coming to this, as I told that it is going to generate two types of classified output: spectral angle mapper classified output, that is with colorful classified map. Along with that, rule images will be generated, and darker pixel is considered to be the best match. So this is one of the popular institute at Dehradun, that is Forest Research Institute. And here you can see in this location the grassland feature is there. So darker pixels are better match. Near to this FRI there is an urban area. So here it is darker. In this near to FRI there is a forest patch. So this forest patch is appearing darker. So you can see here when we are changing the angle in the spectral angle mapper, like 0.02 radian minimum angle, few classes got classified. When we increased this to 0.05 radians, most of the classes got classified, but many are remained unclassified. And then 0.1 radians, maximum classes got classified, few misclassifications are occurring. And increasing the angle to more, it is false classification is happening over there. So normally it is considered that 0.1 radians is considered to be you can say good you can say measurement of that particular angle, which can be used for classifying the most of the data. This is another example when we took multispectral data and hyperspectral data. Here you can see species level classification is better compared to your multispectral classification. Then coming to another data, I'll be showing it to you that this is the close range hyperspectral data. With that data, we have used various different kind of techniques. We used only one of the spectral angle mapper, then the support vector machine and your MNF based technique, and your we took several parameters and rule based classification we have done. Then how the classification has improved. So in this case, you can see that wherever it is appearing literally very dark and no information was acquired, it was doing a little of misclassification. But when we further used various parameters and we did the classification, it got further improved. Then coming to your this fishtail palm is there. This is your foxtail palm and this is your fishtail palm. So this also got improved further when we took the selected parameters rule-based classification we performed. And here you can see this fishtail palm also got improved when we selected some of the selected parameters we have used for classification. And you can even compare MNF based technique is also improving the classification further. Then coming to this, here we this is your tree trunk. It was misclassified as fur. So this also got further improved here, and this concrete surface is also came properly classified, and this brick wall, which is of the different shades, also got improved further in this classified. Now, only pixel-based classification approach sometimes are not good enough, so we can perform object-based classification also. So with the pixel-based classification, as it is having a little different mixing of the features which is in the background, so it is also coming in between. So that's why misclassification is occurring. So when we took the object-based classification, so it highlighted only that particular classes and rest of the things got suppressed in this. Then sometimes when we have similar spectral reflectance curve for the features, then it is difficult to classify those features. In that case, here we took thermal band also as one of the parameters to highlight the material. So this is when water is there, and this is when your asphalt or you can say shaded area is there of the building. So both the features have similar reflectance value. And you can see this area is actually concrete, and here this is GIC. They also were showing similar reflectance values, but what is happening here is the temperature difference is there. You can see in concrete it is little lower and GIS it is little higher. In this water is lower, asphalt shaded is higher. So when we consider this as one of the parameters, when we classify it here, this is the Sabarmati riverfront, which was actually your concrete surface in this area. It was misclassified as GIC, which got further improved when we use the particular temperature data. In this case, in some of the asphalt area that road and water pixels were coming, with the use of temperature data, it got further. Then coming to the spectral feature fitting technique. In spectral feature fitting, as I told, absorption parameters are very important. So here we try to match the shape and depth of the absorption with your reference data. Means target spectra, your image spectra is there and your reference spectra is there. We have to match the depth of the feature, depth of the shape of the feature. Once it will match, it will go to that class. So here, this is the Cuprite Nevada data of every image. So here, wherever alunite is there, we generated root mean square image of alunite. Wherever alunite is there, so here in this case, bright is considered to be good fit and dark is no fit. Now coming to the spectral unmixing. Why we need to do the spectral unmixing? So first you have to understand the mixed pixel. Normally more than one feature present in a pixel is called as mixed pixel. And mixtures are also of two types, linear and non-linear. Linear is what? Whenever incident energy is coming and separately output is going, that is your linear mixture. Here when linear features are coming and it is going towards the sensor, that is your non-linear mixture. So in this case, you can see with your feature, there are two features. Your B is this vegetation, this A is soil. So when 60% of A and 40% of B happen, so what will happen? It is going to have both the natures of the feature, and which is going to be more dominant, that will be more effectively visible in the image. So here you can see the absorptions got reduced here, and in this case, vegetation absorptions are also coming into picture. Now you can understand by this way also that how, as I was telling you in mixed pixel also, we can identify what materials are present. So here there are three features present in a pixel: A, B, and C. A is 25% present, B is 25% present, and C is 50% present. And the absorption position of A is somewhere here, B is somewhere here, and C is somewhere here. If all the three features are present in this image, your spectral reflectance curve of that pixel will come something like that. So by knowing that, we can identify these materials are present in that particular pixel. Here, this is the mixing space. This is your A, B, C existing at different positions. So how to do the linear spectral mixing? So normally you have to solve the linear equation, that is P is equal to RF, where P is equal to the number of spectral bands, which is represented in matrix form. R is the ground spectra resampled, or you can say same number of spectral bands with the data. And here this 1 to n is representing the whatever features are there, classes are there, like water, vegetation, soil, and n number of classes are there, and m number of plants are there. So we know P, we know R, we can generate fractional coefficient, that is weighted fraction coefficient, like for water, vegetation, soil, something like that. So how it is coming into the data, you can see. This is the abundance image generated from the linear spectral mixing. Wherever water is there, it got highlighted. Wherever scrubs are there, it got highlighted. Rest of the things are not coming. Here, grassland is there. Here, vegetation. Here, dry river bed. And here you can see little mixing between urban features are coming because they have similar kind of materials in the urban area. So it will give the score between 0 to 1. G means what is happening is you can something like that means you can consider like this, like whatever features present in that area, it is the linear sum of that is present in that pixel. It may be 0% or it may be 100% or it may be in between. Means if it is water, so it means water is present here 100% and rest of the features are also present with 0%. Okay, so if pure pixel is there, it will be like that. But if it is a mixed pixel, so that fractional part of the score will come in that abundance image. Wherever water pixels are there, will be highlighted. Wherever grasslands are there, they are highlighted. Coming to other technique, that is called as mixture tune match filtering. So in this particular technique, match filtering, the name itself suggests matched filtering. So this is a partial unmixing technique. Wherever whatever end member you want to highlight, so that end member you give, you try to match with the particular image. Wherever it will be there, it will be highlighting that, and rest of the things will be suppressed. Something like you are using a filter and you have to the kernel size is fixed. So that using that particular kernel size, whatever same kernel size material will be there, they will be filtered out, and rest of the things will be discarded. So this produce in this mixture tune match filtering, what is happening here is in match filtering, like we have urban and dry river. So both will appear bright. Now, how to identify which is urban, which is dry river? So in that case, we are using one of the additional parameter in mixture tune match filtering, that is invisibility. So score image, in score image, high score means it is that class. But urban and dry riverbed both are having high score. Okay. Now in that case, we are considering invisibility. So invisibility means the high score will be there, but low invisibility is there. Then that is urban. Otherwise, that is mixed feature. So here high score, low invisibility with 2. So here urban feature got highlighted. Here high score and low invisibility with 2. This particular vegetation species got highlighted. You can see with this example also. This is your score image of vegetation. This is your invisibility image of your vegetation. So high score, low invisibility. This highlighted this particular class. Now coming to the image enhancement, as I told, we can enhance the data by using image fusion techniques. So there are techniques which are able to preserve the spectral information to a larger extent. So here you can see this is the data with 30 meter, and we tried to take panchromatic data of the same wavelength range. So total 19 bands are there. So when we took the data, here you can see this is the spectral reflectance curve, and this is the spectral reflectance curve, which are more or less similar. But here you can see the shape of the building got improved compared to your previous 30-meter. Then, if that is we don't have anchromatic data, then how to enhance the space in the space? So there is a super resolution technique using single frame super resolution technique. With the band's information itself, we are applying the super resolution image processing method to enhance the data. So here you can see this is a data with nearest neighbor resampled, which is the data is actually with 8-meter resolution. We generated 4-meter data. So with 4-meter resample data and 4-meter super resolved output, what we found here is the texture of the vegetation got improved. The edges of the roads, edges of the buildings also got improved. But here you can see it is little blurred or hazy. So after getting improvement, whenever you will classify, the classification will be much better. And second thing also we observed here is what? This area is actually, you can see this is a soil or a ground. But here it was misclassified as China. So when we did the super resolution technique, this got further improved to your soil. Then what we can do is we can even perform image fusion with SAR data also. So here we performed fusion with pulsar data with C band and L band. And what we observed here is with L band data and with different level of fusion, pixel level, feature level, and decision level. So with feature level with LOS pulsar data, L band data, it was giving improvement in overall accuracy and kappa. And even decision level also, it was good. And in case of pixel level fusion with C-band data, it was giving a good result. Here you can see this area was actually the, you can say, harvested cropland. So in this case, or you can say barren land. So here you can see it was misclassified. Near to this, no urban areas are there, but it was misclassified here. So this got further improved over this. The vegetation species also near to this got further improved along with the agriculture fields and subsettlements. But here you can see it was misclassified in this particular. Now, what we can do is this is one of the data which we this is a Cuprite Nevada data of Averis NG sensor and ITRES sensor of that is CASI and shortwave spectrographic imager and compact airborne spectrographic imager. So compact airborne spectrographic imager is having wavelength range in the VNIR and shortwave spectrographic imager is considering the entire shortwave wavelength region. So wherever iron-rich minerals are there, that compact airborne spectrographic imager was able to highlight, and rest of the minerals were highlighted in this particular data, and all the particular minerals got classified in every CNG data, which is with your covering entire visible to near infrared to short infrared. And this is the different minerals which we classified, that is alunite, carbonate group of minerals, thicite and smectite. And these are the abundance image which we generated. So wherever the existence of those minerals are there, they got highlighted in this. Then what we can do is there is another technique that is called as multiple end member spectral mixture analysis. So here these are the end member extracted using those techniques. That is also one of the way, or you can say approach to automated end member extraction technique. So here we have extracted end members on the basis of root mean square error, average of that, minimum average spectral angle, and count based technique. So using that, we can extract those end members, and after that, after extracting those end members, you can see these are the end members which we have extracted, and extracted end members we used for classification. So we generated the unmixing coefficient image. After that, we performed the rule-based technique and we generated a classified. So multiple end member spectral mixture analysis gave a better result, and mixing of the classes got reduced with this particular end member extraction, the spectral mixture analysis technique. So coming to the softwares, we can use various softwares for processing hyperspectral data. So NV is one of the software, commercial software. Mostly I have used NV software. ADAS Imagine is also having a module for hyperspectral data processing. Multispec and BIM are open source software. Abhyas software is developed by SAC Ahmedabad. So that is a kind of plugin with QGIS software. That is also an open source software. So most of the processing which I discussed over here, you can use Abhyas and you can process the data. And there are few limitations for hyperspectral data are like sometimes what is happening is fine atmospheric features may be confused with the ground materials being emitted. So that may happen because the absorptions are there. That is because of atmosphere or because of the material. It can be confused. So that can be or that you can have to check. Second thing is data storage, because you know that when you have 400s of bands, hundreds of bands, and you have multispectral 5, 10 bands, so storage and transmission of hyperspectral data is one of the issues. Redundancy, as I already told, there are overlap of information content over the sensor. So this is all about my talk. If you have any questions, you can ask. Any questions if you have? Am I audible?
So this is Prashanti. We have few questions in the question and a box.
Yes, yes, yes. Right now I'm getting.
Yes.
So I have received what can be some best and easy accessible source for this data. So as I told you right now that Avery's NG data which was acquired for Indian sites, you can write to SAT with us and from there you can get the data. So this Avery's NG is recently acquired during 2016 and 2018, phase 1 and phase 2. So these data sets are available with SAT Ahmedabad so that you can place an order and you can get the data for use. Second, Prisma data, which is recently announced by Talent Space Agency, you can write a proposal. They can provide you the access for the data. And Python packages, yes, there are Python packages for processing the data. There are various spectral libraries which are being used because the software which I have shown to you in the simulation thing, so that was used using the Python. See, normally we suggest ground truthing in remote sensing purpose you have to do by your own. Okay, ground truthing is actually required whenever you have to do species level mapping or anything. You have to go for the ground truth collection. Okay. Yes, previously done data you can use previously classified or used reference data as reference, but still I suggest to go the data. I told to you that one of the software Abhyas which was developed by SAC Ahmedabad, this you can use as one of the plugin with QGIS software to use or to process hyperspectral data. And BIM is your European Space Agency sensor software, so that also you can use. Any more questions?
Is there any questions from the audience? I mean, the attendees?
You are asking about the online course. Actually, the user manual for that is already there with the software. You can download it. You can like whatever softwares, whenever you are doing any processing, for each and every software, user manuals are there. So you can use that user manual for processing. So I guess no more questions.
Vinay Kumarji, Dr. Roshan here. I would like to ask one question.
Yes, yes, please.
So how do you see the cloud computing in this aspect? Like, do you think we should focus on
Yes, I
developing our
got your
own internal infrastructure, or shall we move on to the cloud infrastructure? So, what is your suggestion on this?
no. Actually, what is happening here is cloud computing. Normally, why we are using cloud computing? First question is that. So we are using cloud computing to. We don't want any software to be there. We don't want any computer dependency. We don't want any data dependency to be downloaded. Okay. But in case of hyperspectral data, we have to process only a single scene. Okay. In case of time series analysis, then that will be a good way to use cloud computing platform. And yes, you can use the same data, but for processing single data in cloud computing platform is not that good enough. Because why we want to do that? When you have a limitation in the system which we are using, and in cloud computing platform, in the cloud only we are using the software, we are writing the codes and all, and we are processing and we are generating the output. But single data, using single data processing, so for that, I don't think that is a good decision to process in cloud platform. Like we have done the time series analysis using SAR data. We have done time series data temporal analysis in the Google Earth Engine platform. But with the hyperspectral data, we haven't explored. And even I think we can download the data, but only processing, because earlier Hyperion data or only Hyperion data was openly accessible. So with Hyperion data, single and very small swath data, I don't think it's a means you can process. It is like some similar kind of software on some similar kind of platform, but I don't think it's a not of that kind of use. I mean, as per as I think and as far as I have seen.
Okay, thank you. There's another question. Sir,
Yes.
is there any open source repository link or source from where you can have a close look on your work or similar works?
My work, if they wanted to see, let me tell you. Anyways, we actually used to conduct hyperspectral courses at our end also in EduSat platform, or in ResearchGate and other things. We can even some of the thesis is available at IRS website, and my some of the papers are published, and few of the works which I have shown to you, that is under publication. So maybe in this year or maybe by next year it is going to come, but open repository kind of thing is not there. Yes, one of the thesis of simulation of hyperspectral data, this is publicly available, and the paper is also published in IEEE GRASS conference, so that also can be seen.
Okay. The email ID. I have observed that you have used pan image for reducing spatial resolution in many
Yes, and
hyperspectral
secondly, we have
sensors.
also performed single frame super resolution technique also. Whenever you are using pan data, not only pan data, we even perform with multispectral data also. So multispectral means like for example, your hyperspectral data is with 30 meter, and nowadays we have Sentinel-2 data with 10 meter. So what we can do is we can take the blue wavelength range, green wavelength range, and red wavelength range for hyperspectral data, and we can also fuse that particular ranges, and we can do the layer stacking of that, and we can use that for further analysis. Somebody have asked, can the use plan image for many and plan wavelength for not cover the full? Uh, See, you are. Can I know, is there any technique to use plan for reducing the spatial resolution? For reducing the spatial resolution, you can do the downsampling of the data. You can just resample it to the coarser resolution. That you can do. And coming to the common wavelength range that I already told, you can use multispectral data of high spatial resolution, and you can do the fuse. My email ID is already, I think, there in the front side. And if you want, you can write my Gmail ID. That is vinay@gmail.com. Anything
Okay,
else?
I think
I think no more
thank
questions
you.
now.
Yeah. Thank you, Vinay Kumar ji. Thank you so much for giving this very fruitful lecture. I hope all the attendees have kind of learned kind of data sets what we are working on. It's been very kind of you to join this. I think the moment Mary Kuti ma'am has asked you and you have been very kind to accept to come and deliver this lecture. Thank you again.
Okay. Thank you so much.
Thank you. Thank you.
So I will request the participants. So you can just have a lunch break now, and you can come back and join around 2:45. Our next session starts at 3 o'clock. Yeah. Thank you.
Okay, we request all the attendees to please go have lunch and come back by 1:45, 2:45. Our next session is about to start at 3 o'clock. Very interesting session is coming up from professor from Italy. So hope we'll see you at around 3 o'clock. Thank you. So we'll keep this session on. This meeting will be on. So whenever you're free from your lunch, please join us. Thank you.